Good day, everyone. So for today class, our topic will be all about dosage regimen design. So basically class, one of the most important job of pharmacists is to design dosing regimens. Okay, it's our job class to inform our physicians on what's the proper dose and the proper dosing frequency of certain medications, especially drugs with very narrow therapeutic windows. Okay, so that our patients class will be able to avoid toxicity and make sure that the patient is receiving the right amount of drug. So for today's topic class, we will be having the following. So we will be discussing about dosing regimens, the IV bolus dose model. Okay, then we'll be talking about the steady state during multiple dosing. So what happens here? Okay, or how do we reach steady state upon giving the drug multiple times? So how to do dose adjustments. Okay, and then lastly, we will be talking about continuous and intermittent IV infusion. So what's the difference between the two? So at the end of the lecture class, the student should be able to first understand the concepts of designing dosage regimens. Okay, so what are involved, or what are the kinetic parameters or the data that we need to be able to do dosage regimens design? Okay, so what are the patient factors that we have to consider and stuff like that? Okay, the next is to understand how drugs accumulate after multiple dosing. Okay, so as you remember class, whenever we give the drug multiple times, it comes to a point wherein the drug reaches a steady state concentration. Okay, wherein we say that the amount of drug being absorbed is equal to the amount of drug being eliminated. Okay, then explain how drugs achieve steady state concentration, its application in dosing. Conduct basic computations on dosing regimens. So basically, I will be teaching you guys how to compute for dose. Okay, then actually if you already know the formula for how to compute for dose, you can extrapolate from that formula the formula for dosing frequency, say for example, and so on and so forth. Then understand the concepts of IV infusion dosing. So we will be discussing here, class, about the difference between continuous IV infusion versus that of intermittent IV infusion. So what's the advantage and disadvantage one from the other? Okay, then conduct computations on dosing regimens given via continuous and intermittent IV infusion and apply these concepts in pharmacokinetic decision making. Now, oftentimes, class, the decision making that we do here simply falls under whether or not we proceed, okay, with a certain dosing regimen, okay, or change the dose, change the dosing frequency, okay, and so on and so forth. So we in this pharmacokinetic decision making class, we decide whether or not the drug is still safe for the patient. Okay, would the concentration still be effective for the patient? Okay, based on the data that we get from the patient themselves. And with that, let's start with the first topic for today. So dosage regimen class can be defined as a manner in which the drug is taken. So oftentimes class, a single dose would be enough to provide an effect. Okay, a single dose of a drug. However, class, most often than not, illnesses tend to last for a certain period of time. Say for example, infections could last for 7 days. So therefore class, if we want to make sure that that infection goes away, we need to provide a treatment that we can give multiple times to make sure that the concentration of drug in the patient is still at optimal levels, okay, or is at therapeutic levels. So in such cases, drugs are required to be taken on a repetitive basis over a period of time, and that's where dosage regimen design comes into play. So multiple dosing class achieves and maintains drug concentration in the plasma or at the site of action that are both safe and effective within the therapeutic window for the entire duration of therapy. Now, class, if you can still remember, this one indicates a single dose. Okay, single dose. Right? How did I know that there is only one dose here, and the drug was only given once? Because we only have one peak. Okay, and we say this is the Cmax. Okay, unlike class, if you give the drug multiple times, you'll see multiple peaks here. Now, when we give the drug class multiple times, we want to make sure that the drug, okay, once it starts to reach steady state concentrations, that steady state concentration remains within the therapeutic window. So sabi natin, this is the MEC and this is the MTC, minimum toxic concentration. However, class, a more appropriate term in terms of dosing regimen design, okay, we usually replace this as minimum safe concentrations, or we call that the MSC. Okay, the minimum safe concentration. Okay, that's the more proper term being used when we're talking about dosage regimen design. Pero when we're just talking about therapeutic window, usually MEC, MTC. Okay, pero in our case, let's just say it's the MSC. Okay, the minimum safe concentration. Now, some approaches class dosage regimen could fall under the following. Okay, it could be empiric. Ito yung madalas na ginagawa ng mga doktor natin. When we say empiric class, it's designed by the physician based on empirical clinical data or personal experience. Halimbawa, napansin niya na ang 500 mg ng paracetamol effective kay patient A. So, pag dumating si patient B having the same complaints, yun din ang gagamitin niyang dose. Okay? At saka frequency. Kung 500 Q4 or every 4 hours, then si patient B, 500 mg din every 4 hours din. So, it's based on personal experience and clinical observations. So, oftentimes, class, it's not that accurate. Okay? Another one, class, would be the individualized dosage regimen. So, this one is based on pharmacokinetics of the drug in an individual patient. So, meaning, class, i-determine mo talaga kung how well is the patient clearing that drug. Okay? Ano yung elimination half-life ng gamot based on that patient alone. Kasi oftentimes, class, the data that we find in drug literatures, okay, these are what we call population-based data. Okay, meaning, kumuha ko isang population, ginather ko, kinuha ko isa-isa ang kanilang kinetic parameters, tapos, sinum up ko, kinuha ko yung mean, at yun ang pinapublish ko ngayon sa drug lit ko. So, it's based on population. So, oftentimes, class, what we get on our drug leaflet is not applicable for our individual patients, not all the time. Okay? So, if you want to make sure, class, that your dosing is very accurate, okay, then we do the individualized dosage regimen. However, of course, class, this would entail costs. Okay, this is very expensive. Why? Kasi maya kukuha ka ng plasma concentration sa patient. So, kukuha ka ng dugo, at the same time, gagamit ka ng specialized equipments to determine the total amount of drug in that patient after a certain period of time. So, medyo mahal to. Okay, kaya most often than not, class, we always go for the empiric dosage regimen. Okay? Or most physicians would opt for this. Kasi hindi naman afford lahat ng patient magpakuha ng dugo at magpa-analyze ng kanilang plasma level concentrations. Okay? So, another approach, class, would be the dosage regimen on population averages. Now, ito yung mga dosing na ginagamit natin na nakasulat sa sa druglet natin. Okay, so this one is most often used. If you want to achieve a balance between cost effectiveness at the same time accuracy in designing your dosage regimen. Okay, so there are two types. We have the fixed model and then the adaptive model. Fixed model is calculated based on population average pharmacokinetic parameters. So ito yung naka-state na agad sa druglet na ito dapat ang dose na gagamitin mo per kilogram body weight, say for example. Okay? Sa adaptive model naman, this one is based on both population average pharmacokinetic parameters of drug and patient variables like weight. Okay? Hindi lang weight, kino-consider pang age, body surface area, hindi lang yon. Consider din dito kasi ang kidney function. Okay, so dito na ngayon papasok ulit si creatinine clearance. Kumbaga, mag-a-adjust ako ng dose ko based on the patient's creatinine clearance. Okay, meron din liver function. Oops. So, based on the patient's liver function, okay, I'm going to adjust the dose of the dose being taken by my patient. Alright? So, that's called class adaptive model. Kumbaga, may mga parameters pa akong, I have other parameters to consider before I give the dose to my patient. So, this was most widely used. Kasi again, it's inexpensive. Kasi si drug manufacturer na ang nag-determine ng average population pharmacokinetics. Okay, then you just use patient variables like the weight, age, body surface area, kidney function, liver function, to adjust the dose based on these parameters. So at least kahit papano you get a good balance between cost effectiveness and accuracy in your dosing. So when calculating multiple dosings, okay, oftentimes, class, this usually the pharmacokinetic parameters being used for multiple dosing regimens comes from the data obtained from a single dose drug study. Okay? Kaya, class, sa ating lectures in pharmacokinetics, di ba ang ating AUC is always just a single dose. Titingnan mo, pag angat, okay, so single dose lang yan. Kung yan ay extravascular, titingnan mo paano umangat, gaano kabilis umangat, gaano karami ang nakapasok sa katawan before siya nag-eliminate. Kasi pag eliminate niya, is it following a first order process or a zero order process? Or kung IV, okay, how steep is the drug declining? So class, kumbaga, ang pharmacokinetic data natin usually nanggagaling sa isang single dose study. Alright? Tapos i-extrapolate natin yung study na yon sa ating patients. Okay? Tapos nagtitake ng drug na yun multiple times. So with these pharmacokinetic parameters and knowledge of the size of the dose and dosage interval, okay, the complete plasma level time curve or the plasma level may be predicted at any time after the beginning of the dosage regimen. Now that's the reason why, class, one of the two most important parameters in multiple dosing or dosage regimen design is the dose and the dosing frequency or the dose interval. All right? These two, class, are very important because, again, whether or not the drug will stay in the therapeutic range will depend on the dose and the dosing interval being used. Okay? Pero underneath this, class, marami pa tayong factors na kailangan consider dyan, syempre. So, the primary would be dose and then the interval. Dosing interval. Pero underneath all of this, syempre, andyan pa yung VD, okay, elimination rate, half-life. These are things that we have to consider. Okay, andyan pa syempre clearance. Okay, so marami pang parameters na kailangan kong makonsider. Okay, ano yung desired CPSS or the CPIC at steady state. Okay, those are other things that I have to consider to get or to be able to arrive to a dose, a desirable dose and a desirable dosing interval that will fit the needs of my patient. Okay? So, kumbaga, class, pag as a pharmacist, ang ibibigay lang nating data sa doctor natin ay yung dose saka dosing interval. Doc, bigay mo siya at 500 milligrams every 12 hours. Yan po ang optimum therapy for our patient. Yun lang ang sinasabi natin. Pero underneath that, ang dami natin kinonsider pang mga parameters like VDK, half-life clearance, mga ganyan. Okay? Just to arrive on those two important parameters for designing a multiple dose or designing a dosage regimen. So class, again, the parameter involved here is the dose, okay, the dose and the frequency. So in terms of dose size, class, so it's the quantity of the drug administered each time. Now, if you give kasi, class, a too small dose, okay, or the dose profile is too small, okay, oftentimes, class, ang nangyayari dyan, it's going to be subtherapeutic. Okay, so yes, there will be minimum fluctuations between the peaks and the trough. We say, ito kasi yung peak, this is the peak, this is the trough concentrations. Okay? Now, class, alam naman natin, di ba? We've discussed this previously, that for you to reach steady state concentrations, steady state, class, is kapag pantay-pantay na yung peaks na pinoproduce ng ating gamot every time we administer the drug. Kasi at CPSS, or steady state plasma concentration, we say that the amount of drug being absorbed is equal to the amount of drug being eliminated. Ka equal Ke. Okay? This is, of course, for extravascular route. Okay? At this point, class, the total amount of drug being absorbed is equal to the total amount of drug being eliminated. And this is achieved after 4 to 5 half-lives. Alright? So, class, sinasabi natin minimum fluctuations kapag konti lang ang difference ng peak concentrations sa trough concentrations. And you achieve this normally if you give the drug at a low dose. Ang problem lang, pag masyado naman mababa ang dose na binibigay mo is, it's not going to reach, or it's not going to create desirable effects. Hindi niya kasi maabot ang minimum effective concentrations. Now, what if naman too large ang dose profile? So, sure, okay, you're going to get the desired effect, pero at the same time, you're going to get the toxic effect as well. And you'll see larger fluctuations, class, between the peaks and troughs. Okay? So, ang laki ng difference between your peaks and your trough concentrations. Alright? So, the optimum dose profile, class, of course, would be the one that provides you a concentration wherein it stays within the minimum safe concentration and the minimum effective concentration. So, sabi nga natin, class, within this range, we call this a therapeutic range, we assume that the drug is both safe and effective. Okay? Kaya, today, class, ang gagamitan ng term is, instead of MTC, the minimum toxic concentration, we'll say that it's the MSC, the minimum safe concentration. Okay? Now, how does dosing frequency naman affect dosing regimens? Okay, so it's the time interval between doses. So oftentimes, class, if the dosing frequency is lesser, okay, ibig sabihin mas frequent mong binibigay ang gamot, okay? Or the dosing frequency is larger, okay, as compared to your half-life, right? So there will be large fluctuations, and therapeutically, it's not going to be successful. Why? Kasi ang layo ng dose mo. Kumbaga, class, dahil sobrang malayo ng pagbigay mo ng dose, ang nangyayari is, when you give the next dose, completely wala na yung gamot sa katawan. So you did not create a steady-state plasma concentration. You did not give the drug enough time to accumulate. Okay? Hindi mo siya pinayagang mag-accumulate kasi ang bagal mo magbigay ng next dose. So, syempre, kasi we don't want that to happen. Okay? Ayaw natin sobrang bagal kasi walang mangyayari sa patient natin. So, it's not going to create desirable effects. What if naman kung too frequent? Okay, we're in class, the dosing frequency or dosing interval is actually greater than your half-life. Okay, later class I'll explain this, how half-life and dosing interval plays a vital role in dose regimen design. Okay, if you give a drug too frequent, okay, masyadong mabilis binibigay, halimbawa, ito kanina, Q24. Kunwari lang naman to, Q24. That's every 24 hours. Okay, kunwari class, instead of Q24, binigay mo naman siya Q4. Q4 hours. Every 4 hours. Sobrang bilis mong binibigay ang gamot. Pag sobrang bilis mong binibigay ang gamot, mabilis mag-accumulate yan, syempre. Okay? Kasi, kumbaga, di pa nga na-eliminate ang drug, binigyan mo na agad ng bagong dose. So, anong mangyayari dun? Papatong ng papatong yun. Okay? Papatong ng papatong until it reaches steady-state concentration. So, therefore, class, accumulation occurs at a much, at a shorter period of time. Okay? So, sure, there will be less fluctuations, but it shows both therapeutic and toxic responses. So, sabi nga natin, we want to get the sweet spot wherein usually it's the dosing interval is equal to the half-life. Okay, we're in class, we say that's the optimum dosing frequency, okay, and it's considered to be therapeutically successful. Kasi nasa therapeutic range ang plasma concentration natin, ang steady state plasma concentration. Okay? Again, class, in multiple dosing frequencies, ang lagi natin tinitingnan dito is the steady state plasma concentration. Kasi yan yung concentration we're in, constant na siya. Hindi siya nagpa-fluctuate masyado. Kumbaga, paulit-ulit yung peaks, paulit-ulit yung trough concentrations. Okay? Unlike class, if we give the drug single lang, one dose, usually need natin is CP sub-0 or the initial plasma concentration. So, in this case, class, in multiple dosing, okay, so CP sub-0, usually applicable to single dose. Okay, as we've explained from our previous lectures. Right? Pero pag sinabi CPSS, this is the steady state. Steady state plasma drug concentration, singit na natin. Drug concentration. Okay, this is usually the term used class for multiple dosing. Okay, so single dose versus multiple dose. Okay, now the principle class that we usually use when calculating for multiple dose regimen is the principle of superposition. Okay, naalala niyo sinabi ko kanina, di ba? We usually don't allow the drug class to completely eliminate. Why? Kasi if we allow the drug to completely eliminate, say for example, ito yung plasma level time curve natin, okay, if you allow the drug to completely eliminate, itong MEC, nawawala yung efficacy. So, dapat class, before the drug completely eliminates, we give another dose. Usually, the same dose ng binigay natin kanina. Okay, the first dose that we gave. So dahil nagbigay ka class the same dose and you did not allow the drug to completely eliminate, okay, nagkakaroon tayo ng superimposition. Okay, we're in class the remaining drug here, the total amount of drug there, plus the drug that you're giving right now, okay, papatong yun. Papatong yung concentration na yun. So therefore, umaangat siyang pag ganito. Until you reach, yun na nga, sabi natin, steady state plasma concentration, where amount of drug absorbed is equal to the amount of drug eliminated. So, there are some situations, class, wherein the principle of superposition, okay, does not apply. Especially, class, if, say, for example, there are changes in the pathophysiology of the patient. Okay, nung una, normal ang kidney function niya, tapos bigla siyang nagkaroon ng kidney damage in the course of hospitalization. So obviously, class, dahil nadali ang kidneys ng patient, affected din yung ability niya to eliminate the drug. So therefore, class, the drug could stay longer inside the body, say for example. Or another one, the patient, okay, during the course of treatment, nagkaroon ng edema. So alam niyo naman kas ang edema, di ba? Edema, nagkakaroon ng fluid retention. At kapag nag-retain ka ng fluid, tendency is tumataas ang volume distribution sa katawan, which will again affect, syempre, yung computations natin. Kasi ang computations natin, kadalasan class, is dependent on your VD. Kasi halimbawa, yun na, sa kidney function. Okay? Pag nagkaroon ng decrease in kidney function class, ano expected natin sa elimination rate? Pwedeng bumagal ang elimination rate, causing an increase in your half-life. So, in this case class, hindi ko pwedeng masabi na kapag nagbigay ako ng same dose, same height lang yan ng previous dose ko. Okay? So, hindi ko na masasabi yun. Kasi naapektuhan na ang VD ng patient ko at elimination rate constant. Okay? Siyempre, marami pang factors dito class na hindi ko na mababanggit. Okay? Pero these are the most common. Alright? Or say, for example, another scenario here is na-saturate na yung carrier system. So, obviously, ang superimposition na to class, ang superposition principle applies to drugs following first order process. Pag nagkaroon ng saturation, ano na to? Zero order na. And we know class that once it becomes zero order, ibang-iba na ang computation dito. So, hindi na siya applicable. Hindi siya magiging applicable. So, again class, normally, the computations we do here in multiple dosing regimen, designing multiple dosing regimens, okay, or dose regimen class, is based on the assumption that the patient's kidney functions, okay, kidney function, liver function, and so on and so forth, is normal. Okay? Although class, we can adjust based on creatinine clearance, okay, kidney function, or sa VD, actual VD ng patient. Okay, we can always adjust our dosing regimen using those data. Okay, pero for now, okay, that's a more complicated topic for pharmacokinetics. Let's just stick with the basics muna. Okay, the assumption class is the patient's physiologic functionings, okay, is normal. Okay, yun ang assumption natin throughout the lecture. Alright? At na-assume natin class that the drug is still following first order kinetics. Kasi pag naging zero order kinetics yan, it's going to make our computation a bit more complicated. Okay? So, let's stick with the basics muna. Basic muna tayo. Okay. Now, we've discussed about loading dose na class from our previous lesson, pero pahapyaw lang natin siyang pinag-usapan. Okay? Pero basically, class, when we say loading dose, ginagamit ito to achieve the desired plasma concentration immediately, okay, at zero time. Alright? So, oftentimes. So, a drug dose does not show therapeutic activity unless it reaches the desired steady state. Okay? So, the desired steady state. So, it takes about 5 half-lives. Actually, 4 to 5 half-lives. Pero we assume na lang na 5 just to be on the safe side. Okay? To attain it. And therefore, time taken will be too long if the drug has a long half-life. Okay? Paano kung halimbawa, 1 day ang half-life ng gamot? So, it takes 5 days before niya ma-reach ang steady state concentration. So, ang tagal naman nun. So, therapeutic effect class can be reached immediately by administering a dose that gives a desired steady-state concentration instantaneously before commencement of a maintenance dose. Okay, so oftentimes class, when we give or when we design a dosing regimen, okay, we give class 2 doses. We give the loading dose. Okay, we tell the doctor, ito po loading dose natin. At syempre, sasabayan natin anong magandang maintenance dose. Right? So this is the formula class that we used. Okay, normally it's just the dose equals to desired steady state concentration multiplied to your VD, volume distribution. This is of course for IV push. Pero kung infusion yan, IV infusion, it's usually the rate of infusion divided by the elimination rate constant. Now please take note class, these are the simplified computations. Okay? There is a more proper formula for this. Okay, this is just kumbaga pag nagmamadali lang tayo. Okay, kailangan ng patient ko ng dose, anong magandang dose? O, yan na lang gamit natin formula. Okay? So yun, pwede naman yun. And for the extravascular route class, tatanan lang natin lagi, andyan si F. F would refer to your bioavailability. Oops. Okay? The bioavailability. So is it 90%? Okay, 80% bioavailable. Okay, then of course, dapat in decimal lagi to. So 0.9, 0.8 pag gagamitin siya sa equation. Alright? Okay. So for maintenance dose naman class, okay, usually it depends on the therapeutic index of the drug. Okay, and it's very dependent on the half-life, okay, of your drug. So the formula class that we used here would be clearance times your desired plasma concentration. Again, this is desired. Okay, ano ba ang plasma concentration na gusto kong ma-reach? Siyempre, it should be somewhere within the therapeutic range. Pero most often than not, class, given naman sa druglet natin kung ano yung desired plasma concentration ng gamot natin, or what should be the plasma concentration we should be aiming for specific medications. So, given naman yan sa drug leaflet. Alright? So, when you do computations, hindi ka na manghuhula. Okay? Ang hirap naman, paghuhulaan mo pa kung ano yung desired plasma concentration for that specific drug. Right? And then, of course, if it's extravascular, divided by F. Pero kung intravenous yan, ang F lang naman is still 100%, so that's just gonna be 1. Okay? And then, of course, clearance. Don't forget, the formula for clearance would be VD times K. Alright? So, there are certain generalizations, class, that we can state, okay, with regards to maintenance of the drug within the therapeutic range. So, normally for a drug with a short half-life and narrow therapeutic window, ibig sabihin, ito yung konting taas lang ng dose, toxic na, konting baba sa dose, nawawala na siya sa therapeutic range, okay, such as heparin. Actually, marami namang gamot na may narrow therapeutic window. Okay, normal case dosing frequency is essentially less than your half-life. Okay, and for a drug with a short half-life and high therapeutic index, okay, dosing frequency can be several times that of your half-life, but the maintenance dose has to be larger. Okay, so that you can achieve, or the plasma concentration can persist above the MEC. So, kung gusto mong bagalan ang dosing frequency mo, pwede naman, pero taasan mo ang maintenance dose mo. Alright? These are for drugs with short half-life, okay, and then high therapeutic index. Ibig sabihin, malapad yung therapeutic window niya. So, malaki ang difference between MSC and MEC. Ayun. So, class, this one is very applicable especially for chemotherapeutic drugs. When we say chemotherapeutic drugs, oftentimes ang pumapasok sa isip ng mga estudyante ay for cancer. Okay? Hindi lang naman class ang chemo drugs ay for cancer. Antibiotics are classified as chemotherapeutic drugs. Antivirals are chemotherapeutic drugs. Okay? Anything designed class to destroy, right, certain microorganisms or cell are classified as chemotherapeutic drugs. Okay? Nagkaroon siya ng popularity it became popularly used, the term chemotherapeutic drugs is popularly used for cancer. Okay? Pero it applies to antibiotics as well. Okay, so for antibiotics class, oftentimes they have high therapeutic index, plus short ang half-life. So, minsan nangyayari is, yung dosing interval nila is larger than their half-life. Again, ideal kasi dito class is, dosing interval should be equal to drug's half-life. Pero syempre, hindi naman applicable all the time yon. So, pwede naman kasi mas mataas ang dosing interval ko. Halimbawa, ang half-life ng gamot ko is 4 hours, pero bibigay ko ang gamot ko every 12 hours. Okay, yung dosing interval ko. Pwede naman yon. Basta taasan mo yung dose. Okay, tataasan lang natin yung maintenance dose para above the minimum inhibitory level or above the MEC tayo lagi. A drug with an intermediate half-life may be given at intervals equal to or less than your half-life. Pwede naman. Pero, again, the ideal class would be the dosing interval should be equal to your half-life. That's the ideal. Pero another thing you have to remember, a dosing interval should always be a number that can divide 24 hours. Para maibigay natin ang gamot class same time every day. Okay? Para hindi naman malito. So, you'll never see a dosing interval that is every 11 hours, every 3 hours. Okay? Parang wala ka makikita ng ganyang klaseng dosing interval. It's always every 4 hours, 12 hours, 8 hours, 24 hours. Okay? Yeah. And so for drugs with very long half-lives, such as amlodipine, oftentimes, a once daily dose is very convenient. Okay? Another good example, class, digoxin. Digoxin has a half-life of almost 5 days. Pero ang dosing frequency natin, every 24 hours. Every once a day, di ba? Okay, yun nga lang, anong ginagawa natin sa dose ng digoxin? Binababaan natin, syempre. Okay, para hindi naman siya maging masyadong maging toxic. Alright? Kasi drug stays too long inside the body. If you give it at a large dose, it's going to cause toxicity. Now, let's talk about dose ratio, class. What is this all about? So, dose ratio, class, oftentimes, ginagamit to determine the degree of accumulation. So, usually, it's the ratio between the loading dose and maintenance dose. So, usually, ang loading dose mo divided by the maintenance dose. Now, normally, class, ang sinasabi lagi natin, di ba, ang loading dose ko should be twice that of the maintenance dose. Kasi ang goal natin lagi dito, class, is to have a dose ratio that's equal to 2. Right? Yun yung goal natin. So, normally, halimbawa, kung ang maintenance dose ko is 500 milligrams, ito yung maintenance dose ko, normally, ang loading dose ko would be 1,000 milligram. Kasi yan ay, so, dose ratio, okay, di ba? Loading dose divided by maintenance dose. So, 1,000 yan, divided by 500 milligrams, and you get 2. Okay? Now, that's a good dose ratio. Right? Yun yung goal natin. Now, normally, class, ang dose ratio kasi, technically, it doesn't really depend on the drug. Okay? The degree of, the dose ratio, yes, it depends on the dose of the drug, kaya nga dose ratio. Okay? Pero kasi the degree of accumulation, okay, how well is the drug accumulating, is basically dependent on 2 factors. It's the dosing interval and the drug's half-life. How often are you given the drug? Okay, and what is the drug's half-life? Kasi kung titingnan nyo, class, halimbawa ito. IV na lang tayo. So, kung ito yung 100%, ito kunwari 50%. Ito yun, 50%. And this is your half-life. Normally, class, okay, pag wala akong ginawa dyan, single dose lang, the drug will just simply eliminate. Okay, it's just going to eliminate. However, class, if I give another dose here, okay, I'm preventing it from eliminating. Basta I give it at the same time every day, okay, or at the same dosing interval, same dose, okay, sooner or later it's going to reach steady state concentrations. Okay, and that would give you a dose ratio, class, that's equal to 2. Okay? Most often than not. Now, class, if the dose ratio, if the dose ratio is smaller than 2, oftentimes, nangyayari ito if your dosing interval is greater than the, dosing interval is greater than your half-life. Okay? Then the degree of accumulation would be lower. Okay? It's not going to accumulate that well. Okay? Now, if the dosing interval is less than, okay, if the dosing interval is less than your half-life, ang tendency naman dyan, it's going to be greater than 2. So, therefore, it's going to cause a higher degree of accumulation. Okay? So, kumbaga, you're giving the drug kasi much quicker than paano ba ito sabihin? Mas mabilis mong binibigay ang gamot kaysa sa capacity ng katawan mo na i-eliminate yon. Right? So, therefore, you're giving the drug more frequent. Okay, in this case, right, kasi less than half-life siya eh. Okay? So, you're giving the drug more frequent. This is more frequent. So, therefore, class, it's going to cause accumulation. Unlike here, when the dosing interval is greater than the half-life, meaning less frequent mong binibigay ang gamot. Halimbawa, half-life niya is 12 hours, pero every 24 hours mo binibigay. Aba, hindi talaga mag-accumulate yun. Kasi kumbaga the next dose na ibibigay mo, wala na yung gamot sa katawan. Na-eliminate na. Alright? So, yun, class. Again, dose ratio usually is just another means for us to check kung the drug is accumulating well in the body or not. Alright? Again, class, in terms of degree of accumulation, the dose doesn't really play that much of a role here. Okay, the degree of accumulation. What plays a major role here would be the dosing interval and your half-life. Okay, how often are you giving the drug, and how well is your drug being eliminated from the body? Now, again, class, normally stated sa drug lit ang half-life ng gamot. Pero again, yung half-life na yun is based on a population with healthy kidneys, healthy liver function. Alright? Yun yun. Okay, although some manufacturers class do, some researcher, drug companies would usually check for what's the population estimate for people with kidney diseases. Okay, they do that. Pero again, hindi natin pag-uusapan yun dito. That's more on clinical pharmacokinetics na. Okay, again, ang assumption natin dito, lahat normal. Okay, everything is normal. Alright? Yun. So again, that's for dose ratio. Okay, it's simply the ratio between loading and maintenance dose. And in terms of degree of accumulation, we look at your half-life and dosing interval. The magic number is 2. Now let's talk about class the IV bolus dose model. So why are we going to talk about this prior to other discussions? Because again, class, it's the simplest example of a multiple dosing, okay, model. Alright? A multiple dosing model. Mas madali siyang intindihin kumpara sa infusion at saka sa extravascular. Usually, extravascular class is just an IV bolus dose model, okay, nalalagyan mo ng bioavailability factor. Yun lang yun. Alright? Pero for infusion class, mas complicated than this. Okay? But anyway, for IV bolus dose model, it's usually represented by a one-compartment model with first-order elimination. Again, here's something that you need to take into consideration, class. This is a first-order elimination process. Pag zero order na kasi yung drug natin, halimbawa, ang therapeutic concentrations ng gamot is near the saturation point, like phenytoin, warfarin, aspirin, okay, yung 0 watt power natin, theophylline. Okay, then class, hindi applicable yung model na IV bolus dose model. Okay, kasi assumption dito is that it should be following first order process. Okay, so let's have a scenario here, class. Okay, say you're taking a drug given intravenous bolus or IV push. So obviously, class, if it's IV push at 0 time, it's going to be at its highest peak. Okay, andito agad siya sa pinaka-highest point niya. Then it's going to eliminate following first order kinetics. Kasi sabi natin, it follows one compartment model, first order elimination. So therefore, class, yung peak dito, since we're going to give this multiple times, okay, let's label it as Cmax 1. Okay, it's the first Cmax because we're going to have many Cmax here because I'm going to give the drug multiple times. Pero kung single dose lang to, if this is a single dose, usually it's just CP sub 0. Now, normally, class, and then this will be Cmin 1. Now, normally, if I don't give another dose, allow it to eliminate, parang single dose lang to, right? It's going to eliminate following first order kinetics. Pero sabi natin, if you want to maintain the effect of a drug, okay, don't allow it to fully eliminate yet. Okay, before it totally eliminates, give another dose. Okay, usually, class, yung dose na bibigay mo dito will be the same dose as what you gave in the first one. Right? So therefore, class, this time, it's going to be labeled as Cmax 2. Now, why is Cmax 2 higher than Cmax 1? Sabi nga natin, the principle of superimposition. Okay, superimpose tayo dito. Superposition. Okay? The principle of superposition. Okay, nagsusuperimpose tayo kasi may natitira pang gamot dito. Okay? May natitira pang diyang gamot. Papatungan ko siya ng bagong dose. So therefore, ang Cmax 2 ko mas mataas kaysa sa Cmax 1. Okay? Then allow it to eliminate again. And then that will be my second minimum concentration. Kasi ang first would be from the first dose. Now, of course, class, the distance between the next dose and the succeeding doses is equivalent to your dosing interval. And that should always be, most often than not, it should be equal. Okay, hanggat maaari. Okay? Now, remember, class, the formula C equals CO, E negative KT. Okay, sorry, hindi ko na siya na superscript. Hindi ko na superscript to. Okay, in this case, class, this one is for a single dose. Applicable to, class, for a single dose, once mo lang binigay ang gamot. Okay? So, dahil I'm giving the drug multiple times, okay, I can change this formula to fit my situation here. Okay? We're in, class, my Cmin 1, right? Diba ito yung concentration at any given time. The C here is concentration at any, given time. C sub 0 here is my initial CP, plasma concentration, or the concentration at time 0. So since I'm going to give my drug multiple times, instead of C sub 0, I'll be using the term C max 1. Tapos class, ang C min 1 is usually the concentration, okay, after the dosing interval. Okay, or before you give the next dose. Yung C min 1 is the concentration that stays inside the body, the patient's body, prior to giving the next dose. Okay? That makes sense. Prior to giving the next dose. Okay? So therefore, class, yun na nga, tau here is simply the time from C max 1 to C min 1. Now, look at here, class. Sabi ko kanina, di ba, before we allow the drug to completely eliminate, that's C min 1, okay, papatungan natin yan ng dose. Okay, ng bagong dose, okay, which is equivalent to the first dose that I gave. So therefore, class, the height of this, okay, of C max 1 plus the C min 1, yung natitira pang concentration sa loob ng katawan ng patient ko, okay, if I add both, I'll get C max 2. Nagets ba? Okay? So kung ba, class, yung natitirang concentration dito sa C min 1, tapos gusto ko malaman ano nga ba yung initial concentration dito. Pag pinag-add ko yung dalawang yan, okay, I'll get C max 2. Make sense? Alright? So C max 2, class, simply C max 1 plus C min 1. Kasi nga, pinatungan ko yung natitirang concentration dito sa C min 1. Right? So I did not allow it to completely eliminate. So yung natitira dyan, papatungan ko ulit ng bagong dose. So since I'm giving this at, say, for example, 500 milligrams, tas 500 milligrams din to, yung dose nito. So expected ko, class, ang height ng C max 2 ko will just be the same as this plus yung pinatungan kong concentration. Okay? So if that makes sense. So that's the formula now for C max 2. Now, I can actually expand the formula here kasi meron tayong formula for C min 1. This one, right? So therefore, class, I'll just put the formula for C min 1 here. So C max 2 is equal to C max 1 plus C max 1 E negative K tau. Okay, again, ito galing lang naman dito yan. Oops, ano yan? Dito. Alright? So dahil C max 1 plus C max 1 E negative K tau, algebraically, class, I can simplify this formula. Okay? And write it as C max 2 equals C max 1 times 1 plus E negative K tau. Alright? And that's the formula for C max 2. So are we good? Now, what if, class, I give the drug multiple times? Okay? So hindi lang C max 2. Meron pa ako dyang C max 3, C max 4, C max 5, C max 6, 7, 8, 9, 10, 100 C max. Okay, kung 100 times kung binigay ang gamot, like maintenance doses. Alright, so haba pa ito ng haba ang formula ko. Haba pa ito ng haba. Okay, luckily, class, we have, okay, a shorter formula for that one. So if you give the drug multiple times, class, okay, you're going to have multiple C maxes. Okay, until you reach steady state. So normally, class, before steady state is reached, okay, kasi iba ang formula ng for steady state, iba rin ang formula para pag hindi pa nasa steady state ang concentrations mo. So iba yung formula to compute for C max there. Okay? So to compute for C max after nth doses, normally, class, we have the formula. This one is before steady state. So that C max n equals C max 1 times 1 minus A negative n K tau over 1 minus A negative K tau. Ano yung n na to? The n here, class, refers to the number of doses given. Ilang gamot na ang nabigay sa pasyente mo. So, syempre, kung C max 4 ang aking ang i-determine, ibig sabihin, yung pang-apat na dose na yon, diba? C max 4, obviously, that's the 4th dose. So, therefore, my n will be 4. Okay? Make sense? Yan. So, yun lang, class, ang pinagkaiba ng formula na yon. Now, kung pagkukabit kayo ng C min n on the nth dose, ano yung ang minimum minimum concentration before I give the next dose, alright? Same formula, class, ng C max. Ano lang dinagdag ko? E negative K tau. Okay? Now, this is actually, class, yung E negative K tau na yan, nanggaling lang naman yan dito. See this? Okay? Instead of E negative KT, kasi ang gusto ko malaman dito is the concentration before I give the next dose. So, therefore, yung T ko, papalitan ko ng tau. At ang C na to would be, of course, C min. Okay? So, are we clear? Yun. So, ang C sub 0 dito is simply my C max n. So, make sense? So, therefore, class, ang formula for C max S, which is C max 1, 1 minus E negative n K tau, ito. Alright? this is equivalent to C sub 0 natin, sa equation natin, sa equation of the line. So therefore, isisingit ko lang siya dito. Okay, tapos dagdag lang ako ng E negative K tau. Now, class E negative K tau again is actually the formula that measures the fraction of drug eliminated in a specific time. Alright? So, kung ba class, this value here, the E negative K tau, or E negative KT, actually kahit ito, E negative KT, okay, it measures class the fraction of drug eliminated in a specific time. Okay, so how much of the drug was eliminated, or how much of the drug is still remaining after a certain period of time. Okay, inside the body. Yun yung formula, E negative KT, or E negative K tau. Alright? Okay, so again, I just want you to understand, class, how we were able to derive this formula. Now, you might be wondering, sir, ano tong 1 minus E negative NKT over 1 minus E negative K tau? Okay, sa next slide ito. Pero, class, this one is actually the formula for the accumulation factor. Again, we are giving these medications multiple times. It's going to accumulate inside the body. So therefore, because it's going to accumulate, we need to identify how much of the drug will be accumulating. So hence, we have the formula for, that's why we have to consider the accumulation factor. Again, class, the degree of accumulation is not really dependent on the dose. It's dependent on the number of, the dosing interval and your half-life. E di ba sabi natin to compute for half-life, you need your K. Alright? Kaya andyan si K. Hindi mo mawala si K. Alright? Ay, class, this is K tau. Please, please correct this. This is K tau. Okay? Hindi yan T. That's tau. Alright? Hindi ko na kasi ma-edit. I don't know why. Pero that's E negative K tau. Sa taas may N lang. Sa baba, walang N. Okay? Walang number of doses. Okay? Yun. Alright. So, class, for Cmin, okay, sabi nga natin, the formula is simply like this one. Cmax 1, 1 minus E negative NK tau over 1 minus E negative K tau. Yan, maayos-ayos na yung formula ko dito. As E negative K tau. Again, fraction of drug eliminated with respect to a specific time. Now, class, the Cmax here, okay, sabi natin, Cmax 1, the first concentration na makuha mo after giving one dose. Di ba sabi natin, class, this is actually equivalent to your CP sub 0 if you're only using one drug. But technically, okay, if I'm going to use only one drug, this is, ayun na nga, Cmax 1. Okay? Now, class, ang formula natin for CP sub 0, alright? So, for CP sub 0, class, is dose over VD. Okay? So, that's dose over VD. So, meaning, class, this formula here, I can replace it with Cmax. Instead of CP sub 0 gagamitin kong term, I'll be using Cmax 1. Tapos dose over VD. So therefore, class, ipasok ko yun sa formula dito, siya rin. Okay, ang formula ko for Cmin N, I have now, okay, would be dose over VD. Alright? Hope that makes sense. Again, ang dose over VD na yan, class, okay, simply galing lang yan sa Cmax 1 or your CP sub 0. So, hindi magic yan. Okay, then sinabi ko sa inyo kanina, itong 1 minus E negative NK tau over 1 minus E negative K tau is simply the accumulation factor. So, following the first dose, if the second dose is given early enough so hindi lahat ng first dose ay nawala, okay, the drug will definitely start to accumulate. Okay? And therefore, class, to determine how much of the drug is accumulating, we need to determine the accumulation factor. And the formula for that is what we have right here. Alright? Okay, so let's have here a sample problem, class. Okay? Compute for the accumulation factor. So obviously, required, sige ba na, basahin ko muna yung problem. Okay, so compute for the accumulation factor if 100 doses of a certain drug are given to a patient where K is 0.05 per hour and tau, or dosing interval, is 8 hours. Then may follow-up question, what about kung 2 doses lang or for 3 doses? Alright? So given, okay, we have the K 0.05 per hour. And then we have the tau, which is 8 hours. Okay? Yan. Tapos ang required would be accumulation factor after 100 doses, 2 doses, and 3 doses. So, solution. So, sabi natin, accumulation factor, formula dyan would be simply 1 minus E negative N K tau over 1 minus E negative K tau. Okay, so that's 1 minus E negative 0.05 times 100 doses. Sulat ko mapala ng tau. Ano nga ba tau natin? 8 hours times 100 doses over 1 minus E negative 0.05 so ito nga per hour times 8 hours per hour. Okay? So kung 100 doses yan, so yung 1 minus E negative 0.05 times 8 times 100 equals, alright, that's simply 1. Ang lalabas dyan is 1 over 1 minus E negative 0.05 times 8. 0.3297. So 1 divided by answer, you get 3.0332. No units to kasi it's a factor. Right? So that's the accumulation factor after 100 doses. This AF 100. What about for AF2? Okay? So same thing. Sige, suot na natin 1 minus E negative 0.05 per hour times 8 hours times 2. 1 minus E negative 0.05 per hour times 8 hours. So after 2 doses, okay, 1 minus negative 0.05 times 8 times 2. You get 0.5507 divided by 0.3297. And you get 1.6702. Okay, what about AF after 3 doses? Same thing. Aba, 1 minus E negative 0.05 per hour. Matrabaho lang magsulat. Times 3 over E negative 0.05 per hour times 8 hours. At ang lalabas ay 1 minus E negative 0.05 times 8 times 3. Charan. 0.6988 divided by 0.3297. It's going to be 2.1195. Okay? So what have you noticed here, class? Oops. Hindi pala lumalabas. Sorry. Sulat ko na ulit dito. It's 2.1195. Natatakpan pa ng mukha ko. Right? So, because what have you noticed here? As you increase the dose, what happens? As you increase the number of doses being given, hindi the dose, okay, but the number of doses given, okay, you can see, class, that the accumulation factor increases. That's what have you noticed here, class? Okay? Dito sa AF100. Patingnan natin yung color muna ng ating pen. Okay, nakakasawa na yung red. Masyadong masakit sa mata. Right? So, what have you noticed here, class? Sa AF100 natin. Okay? You notice, class, after giving it after 100 doses, ano nangyari sa value natin sa 1 minus E negative NK tau? Di ba naging 1? Okay? Para tandaan to, class, ha? Ang numerator na to, usually nagiging number 1 yan. Okay, nagiging 1 na lang yung value niyan if the drug is already assumed to be at steady state. So, are we clear? Okay, yung 1 minus E negative NK tau na yan, nagiging 1 yan kapag yung number of doses na binibigay mo is already expected to reach steady state concentration. That's the reason why, class, okay, in our next topic, which is all about the steady state during multiple dosing, right? What you will notice here, class, is the formula for accumulation factor changes. Okay, so steady state during multiple dosing, class, so the suitable amount of dose and identical dosing interval leads to the steady state at which the mass of the drug administered or absorbed is equal to the mass of drug being eliminated. Alright, so achieve usually after 4 to 5 hours, or sorry, 4 to 5 half-lives reach. Okay, so a while ago, class, notice that the equation natin for accumulation factor is 1 minus A negative NK tau over 1 minus A negative K tau. At steady state, class, ang accumulation factor nagiging 1 na yan. Okay, yung numerator. So it becomes 1 over 1 minus A negative K tau. Alright, does that make sense? Okay, as you've experienced a while ago, class, if you give the drug multiple times na kasi, most likely naman siguro, di ba? If you give the drug 100 times, nasa steady state na yon, malamang sa malamang. Okay, but if you really want to make sure, class, then get the half-life, multiply it to 4 to 5, then whatever, tignan nyo lang kung na-reach na yung time to reach steady state. Okay? So, therefore, class, okay, at C-peak steady state kasi constant na to. This becomes constant. Okay? This becomes constant provided that the rate of elimination doesn't change, volume distribution doesn't change. Okay? Normally, class, constant na yan, basta hindi lang magbago yung volume distribution ng patient ko at yung kanyang kidney function or kanyang rate of elimination. Right? It's going to be constant all throughout. So, at C-peak steady state, class, the formula for this, okay, the C-peak at steady state, is simply dose over VD, which is the Cmax 1, okay, times 1 minus A negative, 1 over 1 minus A negative K tau na lang. Okay, it became much simpler. Okay, as compared to the computation kanina, wherein the drug is not yet at steady state. Okay, and then obviously, class, the C trough at steady state, similar lang naman. Ano lang dinagdag natin? Yung fraction of drug eliminated. Okay, after a specific time. Okay, fraction of drug eliminated. So the trough occurs just before the administration of the next dose starts. Okay? So usually, class, at this side here, wala pa yan sa steady state. Normally, at steady state, this is already after 4 to 5 half-lives have been reached. And class, it's more practical to get the peak concentration at steady state kasi steady na. Yan yung mini-maintain mo na lang eh. Kaya nga, class, oftentimes, if you want to take blood from your patient, okay, analyze it for drug concentrations, you always get the drug concentrations, class, at steady state. Okay, kasi dito, consistent na yung plasma concentration ng patient natin. Kaya nga, importante dyan na i-compute mo how long does it reach. Okay, how long should you wait to reach steady state? Again, it's just 4 to 5 half-lives. Okay, your drug's half-life multiplied to 4 to 5. Okay, to be on the safe side, just multiply it by 5. Alright? Para yun ang sabi mong oras. Doc, sa ganitong oras, na steady state na, pwede tayo kumuha ng gamot. Pwede tayo kumuha ng dugo sa patient natin to analyze for drug concentrations. Okay, so let's try this one, class. If Cmax 1, K, and tau are 100 milligrams per liter, 0.4 per hour, and 6 hours respectively, what is the value of Cmax 2? Now, in this, and then may follow-up pala. What about the value for Cmin 2? Now, you can use the formula kayo na class ng Cmax 2, pero I prefer the shortcut. Hindi na shortcut. Okay, yung given nating formula for Cmax n. Okay, so sulat na natin yung given natin. Meron tayong Cmax 1. Given ang Cmax 1 natin, which is 100 milligrams per liter. Our elimination rate constant is 0.4 per hour. And then ang tau natin is 6 hours. Our ating dosing interval. Okay? Ang required sa atin to compute would be Cmax 2 and Cmin 2. So unknown, unknown. So solution natin dyan would be Cmax n equals Cmax 1. That's the accumulation factor, which is 1 minus E negative n k tau over 1 minus E negative k tau. Okay? So obviously, ang n ko ito will be 2. So Cmax ko is 100 milligrams per liter times 1 minus E negative 2, kasi Cmax 2 tayo, times K, which is 0.4, times tau, which is 6 hours, over 1 minus E negative 0.4 times 6. Sorry, hindi na ako susulat ng units class, pero gets nyo naman na ito, di ba? Okay. Unahin na natin yung, 1 minus E negative 2 times 0.4 times 6 over 1 minus E negative 0.4 times 6. Okay, so this is 100 milligrams per liter times 1.0907. Okay yan. Okay. So yun yung accumulation factor. So times 100, obviously, you get 109.07 or 109.1 milligrams per liter. So this is my Cmax 2. Correct? Okay, and then to get for Cmin 2, obviously you just need Cmax, your Cmax 2 times its elimination fraction of drug eliminated. Okay, so therefore Cmin 2 simply Cmax 2 times E negative k tau. So that's 109.07 times E negative 0.4 times 6. Negative 0.4 times 6. And you get 109.07 times 0.0907. And the answer would be 9.89 milligram per liter. Okay. So are we good? So that's how you compute for this class. Again, applicable naman to kung kahit ilang dose pa ang hingin sa inyo. Okay? So bibilangin nyo lang ilang dose na ba nabigay sa patient ko, nasa steady state concentration na kaya. Kung hindi ka sure kung nasa steady state concentration na, be on the safe side, use the formula for Cmax n. Okay, wherein ang accumulation factor is 1 minus E negative n k tau over 1 minus E negative k tau. Okay? Okay. Here's another one. Right, para mapag-practice kayo ng bonggang-bongga. Right, so what's the max concentration after 15 doses if the dose is 800 milligrams and the volume distribution is 20 liters? Assume that tau equals 6 hours and k equals 0.5 per hour. Right? I think kaya nyo na to. Okay, subukan nyo to class sa inyong sarili. Okay, that's 42.1. The answer should be 42.1 milligrams per liter. So pause this video. Okay, try to compute on your own. If you get the same answer, ayos. Okay? Okay. Now, the concentration at any given time after C peak steady state is reached. Now, normally class, ito kasi yun eh. Ito yung formula. So, C peak steady state, E negative KT. Applicable ito class if you want to determine the concentration after steady state is reached. So, kumbaga class, ito. Andito tayo sa steady state, right? Here. Okay, this is already at CSS, at steady state. Okay, halimbawa, alam ko yung peak. Ito yung peak concentration. Kunwari, gusto ko malaman kung ano yung concentration nito. Unknown. Hindi ko alam kung ano concentration na yan. Kaya ko ma-determine yan. Alright? Kahit before Cmin is achieved, o Cmin SS. Okay? Kasi class, alamin ko lang, as long as I know what time it took. So, halimbawa, in this case, 8 hours. 8 days. 8 days. 8 days. Halimbawa, gusto ko malaman ano yung plasma concentration after 8 days. So, kayang-kaya naman siya. Provided class, I have my C peak. Okay? Ang mangyayari lang dyan, class, is C on the 8th day is simply equal to C peak, which is sabi natin, constant na to. Again, provided that the K and the VD does not change. Walang nangyari sa kidney function ng patient ko or sa liver function. Right, so C peak SS times E negative K, whatever your computed K is, tapos multiply to 8 days. And I'll get the plasma concentration on the 8th day. Alright? Before the next, before Cmin, kunwari. So, are we clear? So, again, class, this formula here is very much derived from our original formula, which is C equals COE negative KT. Okay? Wala namang magic na formula dito kasi bigla na lang nabubuo. Okay? Every value that we put in our formulas have a reason. Alright? Okay. Next one, average steady state concentration with IV bolus dosing. Now, this is very applicable, class, if your drug has a long half-life. Kasi kung long half-life, class, ang gamot mo, ibig sabihin mabagal siya ma-eliminate. So, dahil mabagal siya mag-eliminate, so, saan ba tayo pwede mag-drawing? Dito na lang. So, assuming, class, this is my plasma level time curve. So, kung ang kanyang half-life is long, ibig sabihin, class, ang itsura ng kanyang slope parang ganito. So, every dose, mahaba. Okay? So, to the point, class, we're in, ang difference ng C peak, okay, at saka ng Cmin SS, lagyan natin SS para lang steady state. Okay, the difference between C peak SS and Cmin SS is almost negligible. Okay, apakalit lang kasi ng difference eh. So, in this case, class, we don't get the C peak and the Cmin anymore. Okay, we get what we call the average steady state plasma concentration. Okay, and oftentimes, class, ang formula for that is a lot simpler than the formulas we've had a while ago. Okay, it's usually concentration. Sorry, ang label to is C bar. The average, parang X bar, yung mean. Okay, so this one is C bar. So, that's average steady state concentration is equal to AUC divided by your tau, or your dosing interval. Now, ang formula kasi for AUC, usually kuha ka ng isang nito. Diba, from, sorry, ito. This point to this point, this is actually equivalent to one dose. Correct? This is one dose. So, get the AUC of this. Right? Madali lang naman i-compute yan kung sakali. As long as you have your X values and your Y values. Okay? Then we do trapezoidal rule method, right? Okay? If you still remember how to compute for the trapezoidal rule method. Okay? Di ba sabi natin doon, ang area of a trapezoid is equal to y2 plus y1 divided by 2, or x2 minus x1. So in this case, sa ating case, so the area, ang AUC natin would simply be, just need 2 points, okay, for your y. Usually pick at basta 2 points sa y mo. Okay, this is especially true, class, if it's IV push. Okay? Kasi ito lang yung ko-consider ko na C1 and C2. Yung dulot-dulo na yan. So, therefore, that's just going to be C2 plus C1 over 2 times T2 minus T1. So, bahala na kung paano makumpute to. Okay? So, basta makukumpute mo dyan, class, this is already the area of one trapezoid. Now, AUC, class, may mas simple tayong formula dyan. Okay? Na hindi mo na kailangan tingnan ang concentration na C1 saka C2. So, ang gagawin lang natin dito, simply, the formula for AUC would be dose over clearance. Okay? Easy enough, right? So, since ito ang formula ng class, ipasok ko to, dose over clearance na yan, dito. Palit ko dyan. Ang lalabas, class, is C bar, okay, or average steady state plasma concentration is equal to dose divided by clearance times dosing interval. Now, again, class, applicable lang to for drugs with very long half-lives. Okay, not unless, normally in any problem solving that I ask class, sasabihin ko naman kung kung kukuha ako ng C-bar o hindi. Right? Pero in practice, kayo magde-decide. Okay, if you're going to use C-bar, or you're going to compute for Cmax, Cpeak SS, at saka Cmin SS. Okay, in practice, it's upon your discretion as pharmacist. Okay? In our class, sasabihin ko, syempre, para tayo lahat ng sagot. Okay? Okay. So, yun siya. Right, so let's continue now. Now, class, our next topic is about how to adjust dose. Okay? Now, there are scenarios, class, wherein pwede tayo mag-compute ng specific dose natin with an intended plasma concentration. Okay? Pero most of the time, class, or kadalasan talaga, yung intended natin na plasma concentration, hindi natin natutumbok yun in actuality. Okay, minsan kasi hindi natin na-consider, pwedeng may problema ang patient in terms of the way they eliminate certain drugs or their volume distribution inside their body. So, syempre, at least we did our part, right? We tried to assume a proper dose. Pero sometimes, di naman all the time, okay, that dose, class, pwedeng mali. Okay? Nalalaman natin yun kapag kumuha na tayo ng plasma level concentrations, drug plasma level concentrations ng patient after reaching steady state. Okay? So, what do we do to adjust our dose by then? Okay? Now, kasi class, between population estimates versus actual, yung individualized, or actual pharmacokinetic parameters ng patient, kasi tandaan natin, ang pharmacokinetic parameters na meron ako in terms of elimination, volume distribution, etc., pwedeng iba sa inyo. Okay? Madalas, ang ginagawa lang natin is, yung nakukuha natin sa druglet, okay, yun ang ginagamit natin. And that's population-based most of the time. Anyway, so how do we do those adjustments? Okay, how do you predict steady-state concentrations? So sabi natin, class, ito yung formula natin for steady-state concentration. So we already know this. Now, oftentimes, class, you require two main values here. You need a K, the elimination rate constant, and then your VD. And this is usually derived from published reports. But you can also compute for this. But most often than not, class, provided naman to sa atin, population estimates. And these are population estimates. Kinukuha natin sa published reports. Okay? So, let's say, for example, class, we have a patient here, okay, who receives 500 milligrams of drug X intravenously every 6 hours until steady state is reached. Now, just after the dose is administered, a blood sample is drawn to determine the peak plasma concentration. Then, 5 hours later, a second plasma concentration is determined. Now, look at this, class. Sabi natin, most often than not, we can get the K and VD from derived published reports. However, class, if you're given the chance, halimbawa, ang patient mo mayaman, nagpa-determine siya ng plasma level concentration. Sabi ng doktor, kunan natin ko ng plasma level concentration. Let's get your drug plasma concentration time profile. Okay? Payag ka ba, patient? Sabi ng patient, sige, walang problema ang pera. So, class, if you're provided with actual drug plasma concentrations, class, mas magandang gamitin yun kaysa sa population estimates. So, looking at this one, class, you're given two concentrations here. So, just after the dose is administered, okay, so you were able to get a peak plasma concentration here. And since, sabi daw dito, as na yun? Until steady state is reached, so I'm assuming already this is CPSS. Then, meron kang after 5 hours. Okay, yung 5 hours later na yan, yung second plasma concentration, this will obviously be CP after the 5th hour. Okay? 5th hour after the peak concentrations was reached. So therefore, class, I can determine actually K. Okay? Ang gawin ko lang dyan, ln C peak minus ln CP, yung 5th hour, over yung time ko to reach yung peak na ginamit ko sa peak, tapos 5 hours here. Okay? So, sabi nga natin, class, first is to determine your K using the two plasma concentrations given. So, you have the C peak minus ln C5 divided by 5. Kahit diretso mo na divide by 5. Kasi usually, after 5 hours daw from the peak concentrations. So no problem there. Next one, class, you can derive VD from the given formula. So remember this formula here, class. Okay? Ang formula kasi natin kanina, di ba, is C peak SS. Kita ba? Equals dose over VD times AF na lang ha, diretso ko na. Okay? Times AF. So class, obviously, I can compute for VD in this case. Pagpalit ko lang yung position nila dito. So ang lalabas is VD equals dose over C peak SS na yan times accumulation factor. Right? And this is that formula here. So I can compute that for VD kasi meron naman akong dose, kaya na 500 milligrams divided by C peak na na-determine naman daw. And this is the C peak at steady state. Now, class, please take note ha. CP sub 0, it's an estimated value. C peak SS can be determined. Okay, na-determine yan. Nakukuha yan sa dugo ng patient natin. Then third step, given K and VD, we can calculate for a new C peak if we change the dose. Such as if the previous C peak was too high. Halimbawa, ang nakuha kong peak concentration dito was above the MSC. Okay? Above minimum safe concentrations. So therefore, I can adjust the dose. Okay? Provided, class, you have your K and VD. So normally, class, as long as the K and VD does not change, the formula for dose would be this. Again, transpose lang naman to from the equation natin. From the formula na this one. Okay? So ito yung formula for a dose. Provided you have your actual VD, yung computed VD and the C peak, actual C peak. Okay? Or choose a new dose and calculate the resulting C peak. So pwede naman, kunwari, sumubo ka ng bagong dose, kunwari. Gusto mong baguhin yung dose. Tapos gusto malaman kung ano kaya magiging resulting concentration nun. Pwede rin. Kasi using the formula, class, C peak SS equals dose over VD times 1 minus E negative K tau. So are we good? Okay, halimbawa gusto kong baguhin yung dose, yun na nga. As long as you have your VD. Na VD na determine natin sa second step. Okay? Now, class, of course, this will be a little bit complicated, pero at least you get actual data here, or good data here. Now, assuming, class, sorry. Before that pala, so remember that each time we calculate for peak concentrations, we can always compute for the resulting trough concentrations. And the computation for that would be C trough equals C peak E negative K tau. Ito yung C min. C min natin, C min SS. Okay, or C min N. So, depende na kung anong gagamitin nating terms, pero it's just the same. Kasi, class, why do we need to determine the trough concentration? There are drugs, class, wherein we don't look at the peaks to assess for toxicities. We actually look at the trough concentrations. Okay, kumbaga yung trough concentration yung gusto nating ma-maintain at a certain level. We don't care about the peaks. A good example of this, class, would be aminoglycosides and vancomycin. Right? So vancomycin as aminoglycosides. Okay? Dito, class, wala tayong pakialam kahit lumagpas yan sa toxic concentration. Well, titingnan din naman natin eh. Pero the toxicity kasi, class, associated with vancomycin and aminoglycosides is more related to their C trough rather than their C peaks. Okay? So, ang minimaintain natin usually sa vanco at saka sa aminoglycosides are their C trough. Okay, will we do computations here? Regarding this, ni naman. Okay? Pero that's something you need to consider. Alright? So, C trough ang ino-obserban sa kanila. Now, if the dosing interval is not changed, okay, new doses and concentrations are directly proportional if nothing else changes. So, class, say for example, gusto kong baguhin yung dose ng patient ko. Okay? Pero hindi ko babaguhin yung dosing interval. Okay? If you're not going to change the dosing interval, class, instead of undergoing yung process natin kanina, yung nag-compute pa ako ng K, nag-compute pa ako ng VD, ganyan-ganyan. Alright? Kung hindi ko babaguhin ang dosing interval, class, and K and VD stays the same, walang problema ang patient ko, then you can just use ratio and proportion. Okay? Usually, class, ito lang naman ang gagawin dyan eh. Ito yung magiging equation. So, the desired dose will be based on the desired C peak na gusto mo ma-reach. This is the desired CPSS mo. Tapos, ito yung actual CPSS na nakuha mo through by processing the patient's blood. Okay, then just multiply it to the old dose. Okay? So, are we clear with that? Ito yung formula na gagamitin natin dyan. Actually, it's just ratio and proportion. Kasi again, as long as dosing interval does not change, K does not change, VD does not change, then you can just apply the formula here. This formula. Alright? So, let's have a sample problem here. If a patient receives an antimicrobial dose of 400 milligrams IV every 8 hours, now after steady state is reached, a peak level of 15 milligrams per liter is determined. The plasma level 4 hours after the peak is 4.5 milligrams per liter. What dose is required to attain a peak plasma level of 35 milligrams per liter, assuming that the patient has normal kidney and liver function? So in this case, class, andito na, given naman na halos lahat na kailangan natin. We can do this the easy way, or we can do this the hard way. Let's start with the easy way. Okay, ano ba yung mga given muna natin? C peak SS is 15 milligrams per liter. CP after 4 hours is 4.5 milligrams per liter. So we have the time, which is 4 hours. Tau, which is 8 hours. QH siya. Dose, meron din, which is 400 milligram per milligram IV. Alright, so ang kailangan lang naman dito is required dose. That will give 35 milligrams per liter equals unknown. Okay, so hindi natin alam yon. So tandaan natin desired CPSS equals 35 milligrams per liter. Okay, kasi current CPIC niya is 15, so siguro nababawaan yung physician sa CPIC na yan. Kasi optimum, kunwari naman, optimum CPIC is 35 milligrams per liter. So gusto natin i-adjust yung dose ng patient to meet that. Now, provided class, I don't change the dosing interval. Okay, I'll still use every 8 hours. Dose na naman babaguhin ko. Okay, basta hindi magbago ang K at saka VD ko, I won't have any problems. I can use the formula. Solution. Okay, yung kanina, yung XO new equals desired CPSS over old CPSS times old dose. Okay, so ang desired CPSS ko is 35 milligrams per liter. Ang actual CPSS ko is 15 milligrams per liter. Old lang nilagay ko, pero technically that's the actual CPSS. Okay, nagtatamad lang magsulat. And then the dose is 400 milligrams. Ito yung old dose na ginamit ko. So expected ko ito, class, because I'm aiming for a higher CP, tataas dapat yung dose. That's 35 divided by 15 times 400. You get, so obviously, 933.33 milligrams. Now, class, in our quizzes or in my exams, sasabihin ko naman kung usually hinihingi ko is the actual value. The actual na ko-compute ninyo. Pero class, in reality, okay, in reality, this is actually going to be rounded up to 1,000. Okay, ni-round up to 1,000. Kasi ang hirap naman para sa nurse mag-aspirate ng dose, lalo kung vial to okay, na 933.33 milligrams. So normally, class, either you round this up or round down. In my case, I always prefer, again, this becomes a decision, this is a clinical decision by you, the pharmacist, na i-relay mo sa physician natin. Will you round up the dose or will you round down? Again, this one depends on the drug naman eh. Kung malaki ang therapeutic window ng gamot ko, ni-round up ko na yan. Okay, kung alam kong delikado yung gamot ko, okay, minsan nag-round down na lang ako. Tapos check ko na lang kung ano yung magiging possible resulting plasma concentration. Okay? So, ang mangyayari dyan would be, usually, ni-round up ko to 1,000 milligrams. Okay? So, usually, 1,000 milligrams na yan. Now, okay. So, yun yung new dose. Ito yung dose ko. I can actually check, class, kung yung dose na ito, yung 1,000 ko, kasi nag-round up ako eh. Okay? would actually create a problem. So, nagtaas ako, di ba? So, kung pwede mo gawin ko dyan, class, using this formula here, okay, using this formula here, I can actually derive the, yung expected CPSS ko based on the new dose that I'm using. Right? So, usually, class, yung expected CPSS ko would be the desired. Tapos, yung old CPSS, yun yung CPSS na binibigay nung 933.33 milligrams ko. Okay? So, ang gagawin ko lang dyan, class, would be, determine ko lang yung i-transpose nyo lang yung formula. So, that would be desired CPSS times XO old equals XO new times old CPSS. Alright, tapos divide both equations by XO old. So therefore, kasi papalitan ko lang ang terms ko na nagagamit dito ha. This will be resulting CPSS equals adjusted dose times original dose over expected sorry. This is baliktad. Ito yung expected CPSS divided by old dose. Okay? So, adjusted dose ko would be 1,000 milligram times, expected ko dyan dapat is 35 based on sa old dose ko, would be 35 milligrams per liter over the ito yung old dose na ginamit ko, the what do you call this, the original dose. Old dose, original, sorry kasi I hope naiintindihan nyo pa sinusulat ko, is 933.33. Hindi na siya kasya. Okay, so 1,000 times 35 divided by 933.33. Ang lalabas dyan na plasma concentration is 37.5 milligrams per liter. Now, class, siguro hindi naman ganun kalayo siya, di ba? Kasi ang expected ko is 35. Ito yung goal ko. Konting taas lang naman, 37.5. So, I think I can adjust my dose. Instead of 933 ang bibigay ko, gagamitin ko, I'll just round it up to 1,000. In this case kasi, di naman given yung therapeutic window. Pero, just looking at it, class, I think okay na yan. Okay? Pero syempre, in reality, in actual practice naman, alam mo naman yung therapeutic window, most likely nung gamot, right? Okay, just look at the druglet. And doon naman nakasulat yung desired plasma concentration and the therapeutic window. Right? So, gagawin pa ba natin komplikado to? Pwede, pero wag na. Okay na to. Okay? So, why complicate life when you can make it a lot more simpler? Right? So, I hope that makes sense. Okay? Now, class, let's talk about continuous and intermittent IV infusion. Alright? Now, this is actually a more complicated topic than the IV bolus. Kasi sa IV bolus, class, at zero time, nasa maximum concentration ka. If you infuse a drug, okay, at zero time, it's also at zero concentration. So, you're going to, tataas unti-unti yan ang concentration ng gamot depending on how long you are infusing the drug until you reach a steady state concentration. Alright, so it's a lot more complicated than IV push. So, IV infusions, class, are basically used to maintain consistent plasma drug concentrations to achieve consistent effects. And this is like administrating small amounts of drug at infinitely small dosing intervals. So, parang, class, every time na magda-drop, di ba, nakaswero ang patient, every time na babagsak yung isang drop, parang equivalent to one dose yun. Okay, so drop, drop, drop. So you're like giving small amounts of drug at infinitely small dosing intervals. Parang ang dosing interval mo, class, pag continuous IV infusion yan, is yung every drop, every hulog nung gamot na yon. Okay, so kumbaga parang every second, every 2 seconds, yun yung dosing interval mo. Diba? Napakaliit naman nun, right? So plasma concentrations are determined by the rate of drug input, which is abbreviated as KO. Some books would abbreviate this as RO. Kanina sa example ko sa formula natin, RO ginamit ko. Okay, pero mas gamitin lang natin class dito is KO, K sub 0. Okay, VD and clearance. So yun yung mga important kinetic parameters that we need to consider. So KO, VD and clearance. Usually pag may clearance ka, may K naman na nakakakibat dyan. So class, this is how it looks like if you give the drug IV bolus. This is how it's going to look like if you give the drug IV infusion. So parang ganito yan, class eh. If you can zoom in, parang mag-zoom in ka dito, parang nangyari dyan is parang ganito yan. Okay? Each peak na yan is 1 drop. So sobrang dami, right? Okay? Until you reach steady state concentrations wherein ang drug dose mo, class, nagpa-plateau na. Steady na siya. Okay? In this case, class, wala ka na halos makikitang peak and trough. Actually, wala ka talaga makikitang peak and trough if you give the drug continuously. Okay? So, parang each yan, drop per drop, 1 peak, 1 C-peak yan. So, syempre, in reality kasi, you won't see that in a actual plasma level time curve. Makikita mo, class, parang flat lang yan. Okay? Ito lang lalabas sa data natin. Isang straight na curve na ganyan. Straight na curve? Ano yun? Okay, basta curve lang siya ganyan. Okay, wala siyang peaks, wala siyang trough. Wala kang peaks and trough na makikita. Usually, lumalabas yun pag mamaya na. Alright? So, the relationship between a bolus and an infusion, or IV push and infusion, okay, this is how a bolus looks like. If you give it IV infusion, it looks like this. Halos negligible, or hindi mo na, wala kang makikita peaks and trough. Alright? So, it's just going to be a straight line. Now, how do we compute for a dosing regimen if you're giving the drug via continuous IV infusion? So, class, you have to remember, as long as the drug is infusing, it's continuously providing you with medication. Alright? Kaya, di ba may mga infusions tayo, class, that runs for 24 hours. Say, for example, TPNs. Okay, mga ganun. Total parenteral nutrition. There are some drugs given for 24 hours. Alright? Mga nakaswero, ganan. Okay, or di kaya dopamine drip, halimbawa. Dopamine drip, it's going to run for 24 hours until the patient, as long as the patient needs the dopamine, continuous ang infusion nun. Normally, class, we use continuous IV infusions nga pala for drugs with very small half-life. Okay, to the point na hindi ko siya pwedeng ibigay as dito. Hindi ko mabibigay ang gamot intermittently. Okay, yung may dosing interval. Kasi sobrang liit ng half-life niya, like in 1 minute, yung half-life niya is like minutes lang ang tagal. So therefore, you're going to give that as IV infusions. Okay, so the formula used before to determine concentration at any given time before steady state is this one. All right? It's this formula here. That's rate of infusion over clearance times 1 minus E negative KT. Now, class, kanina, diba ang sabi natin, accumulation factor natin for bolus is 1 minus E negative N KT, K-tau over 1 minus E negative K-tau. Yan yung accumulation factor natin for IV push. Okay? Isipin nyo na lang, class, itong value na to, alright? Itong 1 minus E negative KT, parang ito yung accumulation factor. This is accumulation factor for continuous IV infusion. Alright? Para hindi tayo nalilito. Or para mas we can stay on the same page. Right? So parang yun na lang isipin nyo dyan. Actually, hindi yan yun talaga dyan, yung tamang description, pero this is how I usually describe it so that my students can understand. Right? So yan yung, so before steady state is reached, so this is the accumulation factor for an continuous IV infusion. Okay, we're in class, the T here, did I write it down? Okay, so clearance, it's VDK. Okay, and then K sub 0 here is simply the dose administered in a unit of time, given of time, kasi ini-infuse natin to eh. And then class, the T here, okay, this is actually, so the more proper term for this one, class, is the fraction of CSS achieved by time after the infusion is begun. Pero to make it a lot simpler, sabihin na lang natin yan yung accumulation factor for a continuous IV infusion. And the T here, class, refers to the infusion time. Okay, how long will you infuse the drug? Will you be infusing it for 8 hours? Will you be infusing it for 24 hours? Continuously. Ibig sabihin, hindi tumitigil. Okay, so tuloy-tuloy lang yung pag-infuse niya. So that is your infusion time. Alright? Okay. Now, what about the formula used to determine concentration at any given time after steady state is reached? So notice, class, nawala yung accumulation factor natin here. Kasi ang assumption natin dito is at steady state na siya, meaning consistent na yung peak concentration niya or plasma concentration. So therefore, class, the formula will simply be CSS equals K sub 0 or the rate of infusion divided by your clearance. As simple as that. Where the value of 1 minus A negative KT approaches 1. Okay? 1 na yung nagiging value niya. So similar kanina sa 1 minus E negative NK tau natin after multiple dosing is given. After multiple doses are given. Right? So at steady state, class, take note that plasma concentration is directly proportional to the rate of administration, assuming clearance is unchanged. So therefore, CSS is determined by the rate of drug input going in and drug clearance that's going out of the body. So di ba, class, at CSS, we assume that the rate, that the input, which is represented by your K sub 0, is equal to your output, which is the clearance. So are we clear? Kaya ganyan yung formula niyan. So kumbaga, it's a proportionality, right? So yeah, the rate of drug input is equal to rate of drug output. Okay, so let's start off, class, with this problem here, right? So clearance for a drug is known to be 4.5 liters per hour with a K of 0.15 per hour, and this drug is given at a rate of 50 milligrams per hour. Then the plasma concentration after 8 hours after starting the infusion would be, okay, so based on the problem here, class, we're assuming that wala pa sa steady state ang drug natin. So therefore, class, ang magiging formula natin dyan would simply be, the concentration equals rate of drug input over clearance times 1 minus E negative KT. Alright? So ang infusion natin would be, our time here would be, of course, 8 hours. Okay, so this will be the formula na gagamit natin since we're assuming, class, right after daw kasi, the infusion was started after 8 hours. So again, the assumption here would be wala pa sa steady state. Okay, kasi kung sakali sa steady state na yan, matik magiging 1 naman yung 1 minus E negative KT na to. So wala tayong magiging problema doon. So anyway, so let's write now first our given. Okay, so our given, class, are as follows. You have the clearance, which is CL na lang, class, sasalagay ko, 4.5 liters per hour. K is 0.15 per hour. K sub 0, or rate of drug input, is 50 milligrams per hour. And then the time, okay, nag-infuse tayo would be 8 hours. Okay, so ang ating required is plasma concentration on the 8 hour is unknown. So solution, resulting plasma concentration would be 50 milligrams per hour divided by the clearance, which is 4.5 liters per hour, cancel na yan, times 1 minus E negative, K ko is 0.15 per hour times 8 hours. Okay, so unahin na natin to. 1 minus E negative 0.15 times 8. Okay, so it'll be 50 divided by 4.5 times 0.6988. Okay, 50 divided by 4.5 is 11.11. 6988 times 0.6988. And the answer would be 7.7 7644 milligrams per liter. Okay? So yeah, so that's how we got the answer for this one. So 7.8, close enough. Okay? 7.8, 7.76. Pareho lang yan. Almost pareho, I mean. Alright? Okay. That's that. So here's another. If the infusion is continued, the steady state concentration would be, medyo madali na lang to. Kasi di ba sabi natin class, ang CSS is equals to K sub 0 over clearance. And ang ating K sub 0 was 50 milligrams per liter divided by 4.5. Tama. Liters per hour. Tama, liters per hour. Milligram per hour. Ano ba? Okay, so lalabas dyan will be 11.1 milligrams per liter. Kaso itong hours na to. Okay, so I hope that makes sense. Okay, here's another problem. A patient receives IV aminophylline, which has a half-life of 6 hours. O, given agad yung K, pero you can actually compute for this class. Okay, and a VD of 30 liters. Binigay na rin ng clearance. Bait naman ang problem na to. 3.48 liters per hour. Predict the steady state plasma concentration if the infusion rate is 40 milligrams per hour. Okay? So, provided, andyan na rin naman class halos lahat na kailangan natin. So, ang tinatawag dito is predict the steady state plasma concentration. So, again, that's just CSS equals rate of drug input divided by clearance. So, rate of drug input is 40 milligrams per hour. Binigay na ang clearance, which is 3.48 liters per hour. 40 divided by 3.48. And the answer would be 11.4943 milligrams per liter. Alright? So, madali lang naman siya. Kung continuous infusion yan. Nagiging problema to class kapag naging intermittent na. Okay. So now class, let's proceed to the next problem. So a patient is receiving IV theophylline at 20 milligrams per hour. The CSS is 7.5 milligrams per liter and 25 hours was required to reach CSS. Okay? Half-life equals 5 hours. K is 0.139 per hour. Now, if the infusion rate is increased to 40 milligrams per hour, how many hours will it take to reach CSS? Okay? Now, class, looking at this problem, ano ba ang tanong? Okay, kasi you have to think about what is being asked. Kasi kung makikita nyo kasi ang daming given. Okay, in reality class, di ba, ang daming given sa atin. Okay, ang tanong dito is, asan na yun? How many hours, will it take to reach CSS? Right? Binigyan ako dito ng dalawang concentration, and so on and so forth, right? So now, class, looking at the problem, the only question here is, how long will it take to reach CSS? So, ang question dito, ang required dito is, time to reach CSS. Okay, di ba sabi natin, that's just half-life times 4 to 5. Correct? Okay. So remember class, the time to reach CSS, walang pakialam to sa dose na gagamitin mo. Okay, what matters here class is simply the half-life of your drug. Even if I increase the dose, okay, wherein ang original is 20, tas ginawa kong 40, excuse me. So, ang original is 20, then ginawa ko siyang 40 milligrams per hour, okay? Kahit taasan ko pa ang dose class or babaan ko ang dose, hindi naman, basta hindi nagbago ang elimination half-life ng patient ko, okay pa rin yung kidneys niya, okay ang liver function, then class, time to reach CSS is simply 4 to 5 half-lives. So therefore, ano ba yung half-life natin? Okay, 5 hours times 4 to 5. And that would be approximately 20 to 25 hours. Right? So how many hours will it take to reach CSS? Approximately 20 to 25 hours. To be on the safe side, gamitin na natin yung pinakamalaking value. Sabihin natin sa doktor, Doc, after 25 hours na po tayo kumuha ng plasma concentration para siguradong nasa steady state na yung gamot. Again, class, irregardless of the dose, time to reach CSS will always be 4 to 5 of the current half-life of the drug. Okay? In this case, mukhang hindi naman nagbago yung kanyang half-life eh. Kasi assumption natin dito, normal kidney functions, normal renal function. Normal kidney functions, normal liver functions. So, sinabi na rin dito sa problem mo, okay, 25 hours was required to reach CSS. Alright? So, that makes sense. Okay? Okay. So, 20 milligrams for 7.5, that's 40 milligrams. Okay, if we wish to increase CSS to 14 milligram per liter, okay, what rate of infusion should be used? So, kanina class, di ba, ang original rate is 20 milligrams per hour. Ang resulting CPSS is 7.5 milligrams per liter sa problem kanina. Okay, hindi ko na kasi mababalik na ganoon eh. So, anyway, gustong taasan ang new K sub 0. Oh, sorry, not the K sub 0. New CSS. CPSS. It's good. Would be 14 milligrams per liter. So, in this case, class, ano gagawin natin? Mag-a-adjust tayo ng dose. Okay? And remember, class, similar to IV push kanina, okay, provided class that the K and VD does not change, we can just do ratio and proportion pa rin. Okay, so ang formula dyan class would be K sub new rate of drug input, okay, would be equal to ang desired CSS divided by yung measured CSS times the original K sub 0 na ginamit natin. So therefore class, okay, K sub 0 new to achieve 14 milligrams per liter. So, anong desired ko is 14 milligrams per liter. Ang original was 7.5 milligrams per liter. So, obviously, tumaas ang desire ko. So, therefore, tataas din yung rate of drug input ko dapat. Times yung original, which was 20 milligrams per hour. So, 14 divided by 7.5 times 20, you get 37.33 milligrams per hour. So, ito yung magiging bagong rate of infusion ko to get a plasma concentration of 14 milligrams per liter. Now, class, in terms of rate of infusion, huwag kayong mag-alala. Pwede nating gamitin as is kung ano man yung na-compute natin. Okay, kung 37.33, okay lang yan. Alam nyo kung bakit? Meron kasi tayong infusion pumps. Infusion pumps class are smart pumps wherein input mo 37.33, exactly 37.33 milligrams per hour ang may de-deliver niya sa patient natin. Alright? Pero usually sa infusion pump pala, i-convert mo pa to ml per hour. So, how many ml do you need to administer per hour? Okay? So, sa clinical kinetics yung napag-usapan yun. Okay, wag na ngayon. Kasi for now, ang gusto lang natin malaman is yung dose. Okay, how many dose ang binibigay ko per hour. Okay? Pero sabi ko sa inyo, pwede yan as is. Okay, hindi natin kailangan mag-round off. Usually, ang rounding off, ginagamit natin yun sa IV push. Okay? Or di kaya class kung galing sa vial ang drug natin. Ito kasi assume na since it's continuous IV infusion, it's in bags. And dahil nakabag yan, gagamit yan ng infusion pump. Okay? Pero kung old school yung hospital at nagbibilang-bilang yung nurse ng number of drops per minute, pwede tayo mag-round off na dyan. Okay? So, depende na sa inyo yan, ha? Again, this one will depend on your clinical judgment as a pharmacist. Check nyo na lang kung ano magiging resulting plasma concentration kung mag-a-adjust man kayo. Okay? So, alam nyo na kung paano mag-adjust, right? So, using that same formula. Anyway. So, for continuous IV infusion class, here's the formula class if to be used when infusion after CSS is suddenly stopped. Now, ano yung mga reasons kung bakit natin isa-stop ang infusion? Halimbawa, during the infusion, biglang nagkaroon ng adverse drug reaction ng patient. Alam naman, ituloy ko pa yung infusion nun. Okay? So, syempre, I need to stop the infusion. So, assuming class, here's my plasma level time curve. So, kunwari nag-infuse ka dito. Then, suddenly, at this point here, okay, bigla nagkaroon ng ADR ang patient. So, anong gagawin ko dyan? So, I need to clamp my line, may IV line. Lalagyan ko yun ng clip. Kiklip ko yung IV line na yun. Hindi ko puputulin ha, ikiklip lang. Kasi baka may kailanganin ko pa yung gamot, sayang naman. Nakaswear ng patient doon. Alangan tanggalin ko, so babalik ko ulit kung kailanganin niya, di ba? So, i-clip mo yung line. Halimbawa, nagdo-dopamine drip ang patient, tapos biglang ang BP niya tumaas, pero sobrang taas naman ngayon, naging 140, kunwari, 150 over 100. Ang desire mo is 120 lang. So, nag-ADR, technically nag-ADR ng patient na, tumataas na ang BP niya. Sobra na sa desired. So, therefore, clamp. Pagka-clamp ko niyan, obviously, that drug will start to decline following first-order kinetics. Assuming that the drug is following first-order kinetics. So, therefore, class, ang next question dyan is, halimbawa, ito yung MEC. Okay, ito yung MEC. Ang tatanungin lang naman dyan sa'yo ng doktor, okay, Mr. Pharmacist, nag-clamp tayo anong oras? Okay, kunwari lang naman, on the 8th hour. Okay, on the 8th hour. So, Mr. Pharmacist, nag-clamp tayo on the 8th hour. Okay? Kailan ko in-expect na mawawala yung effect ng gamot? Okay? So, obviously, class, para mawala yung effect ng gamot, kailangan bumaba siya ng MEC. Right? So, it needs to go below the MEC. And I can compute for this. Okay, provided class, I know the C peak. Alam ko naman siguro yung MEC ko, right? Okay? Ang determine ko dito, class, would be the time to reach here. This point here. So, ito yung question mark dito. Anong oras yan darating? So, obviously, class, I'll need to compute for, okay, I'll need to have a K here. Normally, yung K ko dito manggagaling sa half-life. 0.693 over half-life. Usually, nasa published literature naman yung half-life. Yun yung gagamitin kong K. And then, class, ang formula na gagamitin ko to determine the time, okay, time. Usually, yun naman tanong dyan ng doktor eh. Time naman, hindi naman technically ang concentration talaga eh. They always ask for, Mr. Pharmacist or Ma'am Pharmacist, kailan ko i-expect na mawala yung effect ng gamot after ko siya na-clamp. Basta alam mong MEC class, madali na lang yan. And provided you know the C peak. So, ang mangyayari dyan class would be T equals ln C peak minus ln MEC. Okay, ano man yung plasma concentration, yung MEC na yan, divided by the computed K. And then you can tell the doctor, Doc, after, say for example, kung ilang oras man yan, ano yung lalawas na solution dito, okay, ganun katagal nyo lang kailangan antayin, Doc, bago mawala yung effect ng gamot. So, are we clear? So, yun lang naman yun. Alright? Pero in this case, class, if you want to compute, for example, from this point here to this point, okay, CP equals unknown. Hindi ko alam yung plasma concentration na yan. On the, say, for example, 10th hour. Hindi ko alam, gusto ko malaman kung ano yung plasma concentration after 10 hours. Then, you can use this formula here. Okay, wherein ang mangyayari dyan is, concentration on the 10th hour will be the CPSS times E negative, kung ano man yung K, times 8. So, are we good? Okay. Pero again, class, the usual questions for pharmacists usually fall under here. Tatanungin ka, anong oras? Gaano katagal ako mag-aantay? Okay, so let's have a sample problem here. Okay? If the aminophylline infusion is suddenly stopped due to ADRs, what would be the plasma concentration after 12 hours? Okay, assuming class that the K is 0.139 per hour and the CSS is 15 milligrams per liter. So again, given naman tayo ng hindi ko lang kasi sulat yung given ha. Pero tanong naman dito is CP on after 12 hours. So therefore, sabi natin CPSS ang naman yan times E negative K T. In this case, 12 yan. So CPSS natin is 15 milligrams per hour times E negative, given na naman ng K, 0.139 per hour times 12 hours. Okay, so ln E negative 0.139 times 12 hours. That'll be 15 times 0.1886 times 15. You get 2.8294 milligrams per liter. And this will be the resulting plasma concentration after 12 hours. Alright, that's the resulting plasma concentration after 12 hours. Okay, so meaning, kung ito yon, graph natin. Kung ito yung infusion ko, pagdating dito, nag-stop ako. Okay. So, allow ko siya mag-eliminate. So, ang tanong lang naman yan is, from this point, 0 na lang. After 12 hours, okay. Yeah. CP 12 hours. Ano daw yan? Okay, so from 15 milligrams per hour, ang CP12 ko after 12 hours would be 2.8 na lang yan. Milligrams per hour. Milligrams per liter. Ano yan? Milligrams per liter. What hours yung sulat ko? Yan, milligrams per liter. Okay? So, yun siya. Now, if the MEC of aminophylline is 3 milligrams per liter, then when would you expect the drug to stop working? So, dito na nga ipapasok yung formula natin kanina, which is T equals LNC peak minus LN MEC over K. Given na rin naman ang K natin. So, LN, C peak natin is 15. Ba't milligram per hour pa nilagay ko? Sorry, milligram per liter. Buti nabawi ko pa. Milligram per liter minus LN under MEC. 3 milligrams per liter over K, which is 0.139 per hour. Okay. So, LN 15 minus LN 3 equals 1.6094 divided by 0.139 equals, there we go. There we go. 11.5786 hours, or usually kasi sabihin ko na yan 12 hours. Mas safe na yung 12 hours. So after 12 hours, ina-expect ko na titigil na yung drug. Okay? Titigil na yung kanya. Yun na. Okay, para katulad dito. After 12 hours, 2.8. 3 hours, right? Okay? Pretty much the same. Okay, so that's that. Now, when we give loading doses class, usually we can give loading dose via infusion. Now, it takes about, 4 to 5 half-lives to reach steady state. So, it's quite lengthy. So, loading dose is given for immediate effects. Okay? So, normally, class, we give loading doses to achieve immediate effects. Yun nga lang, mabilis din siya mawala. Okay, upon administration, the plasma concentration is at its highest. Is at its highest. Okay? Now, when do we not give loading doses? Right? Kaya tayo hindi nagbibigay ng loading dose. If there's a substantial side effect occurring with large dose of a drug. Say, for example, class, antipsychotic drugs. Okay? We don't give loading doses for that for one main reason. At high doses, lumalabas agad yung side effects niya, like extrapyramidal effects. So, if patients, another reason why we won't use loading dose is if patients may require to have adequate time to develop tolerance to the initial side effects, like tricyclic antidepressants. So, you don't want to give it high agad kasi bongga rin yung side effects niya. So, gusto mong mag-create ng tolerance, so unti-unti lang natin. Diba, sabi nga ng kanta hindi sanay sa biglaan. Okay? Whatever. Naisip ko. Anyway, so yung class, you don't want to, you want to develop tolerance, so dahan-dahan lang yung pagbigay ng gamot. So, you don't want to give a high dose agad. Okay, so normally class, actually paulit-ulit na lang yung equation natin here. So to give a loading dose, it's simply the dose desired, the concentration desired multiplied to your VD. Now, you can actually combine class, actually ito naman talaga ginagawa natin eh. We combine a loading dose and an IV infusion at the same time. So if both loading dose and an IV infusion are given, the result would be an immediate and maintained plasma concentration. That's the reason why we give loading dose and maintenance dose. So if this is the MEC, say for example, if you give loading dose alone, okay, ang tendency class is bababa yan below the MEC. But, okay, there's a but. Pagdating kasi dito, wala na yung effect eh. Pababa here. But, kung sinabayan ko ang loading dose ko, pagbigay ko ng IV push, sinabayan ko ng infusion. Okay, before pa bumaba yung concentration na to, okay, before siya mawala, hahataw na yung IV infusion ko, maintaining the plasma concentration above the MEC. Right? So that's the reason why, class, we give drugs. Sometimes, okay, but not all the time, we give it together with a loading dose. Okay? So as loading dose is eliminated, the constant IV infusion should be approximately at steady state. Okay? Now, the resulting plasma concentration, class, if you give a loading dose and a continuous IV infusion at the same time, would be something like this. Okay, ang gagawin mo lang dito, class, is i-combine mo ang formula for a resulting plasma concentration after giving an IV, a loading dose, and the formula for a continuous IV infusion. Alright? So again, ang naman dito is may E negative KT kasi resulting plasma concentration. Okay? Kasi ang formula na to, class, is just simply CP equals CO E negative KT. Ang CO ko dyan, in-expand ko lang, ginawa kong dose over VD. Alright? So walang magic na nangyayari dito. Lahat may explanation. Okay? So yan yung resulting plasma concentration after an IV bolus dose is given. And then ang resulting plasma concentration after giving a drug via continuous IV infusion. So ang VDK na yan is just simply clearance. It's 1 minus E negative KT. So you can combine both, class. Ang lalabas na formula would be ito. XO over VD times E negative KT plus KO over clearance times 1 minus E negative KT. Technically, pinagsama ko lang silang dalawa. Right, so this is the, that's the IV push, and this one's for the IV infusion. Alright? Okay. So it's a pretty straightforward equation, class. Okay, so here's another sample problem. An adult patient is estimated to have a theophylline half-life of 8 hours. K is 0.087 per hour and a VD of 30 liters. If the patient is given a loading dose of 400 milligrams of theophylline and a continuous infusion of 35 milligrams per hour is begun at the same time, what will be the plasma concentration after 24 hours? Okay? So, sige, swap natin ang mga given natin. Ano bang given natin? Half-life. Hindi na. O, yan. K equals 0.087 per hour. May VD tayo, which is 30 liters. Okay, what else do I need here? Loading dose. That was given was 400 milligrams. Rate of infusion was 35 milligrams per hour. Ang time na kailangan ko dito is after 24 hours. Okay? So using this data, I can actually start to compute na. So ang required ko is plasma concentration after 24 hours is unknown. So combine loading dose and maintenance dose. So solution, CP after 24 hours equals, so sa loading dose, that will be dose over VD times E negative KT plus IV infusion, which is K sub 0 over clearance. It's 1 minus E negative KT. Okay. Ang dose natin is 400 milligrams divided by VD ko is 30 liters. Times E negative 0.087 times 24. So, hindi na mo susulat ng ano Okay. Para alam ko na ito ay IV push, ito ay IV infusion. Plus, yeah, plus K sub 0, which is 35 milligrams per hour over clearance to, so that's VDK. 30 times 0.087, oops, times 1 minus E negative 0.087 times 24 hours. Okay, unahin natin to. Sorry kasi diretso ko sa calculator ko ha. Hindi ko na isusulat yung mga chorba. Okay. Times E negative 0.087 times 24. Okay, this would be 1.6523 plus 35 divided by 30 times 0.087 times 1 minus E negative 0.087 times 24. This would give me 11.7480 plus 1.6523, 13.4. 40 milligrams per liter ang resulting plasma concentration ko. So, close enough. Okay? So, pwede na. So, are we good, class? Okay. That's that. Now, some loading dose like theophylline class are not given by IV push. Okay? There are some drugs na pwede mo lang ibigay, ang loading dose niya binibigay as infusion. Bakit? Okay? We give the drug class as infusion because if you give it via push, pwedeng mag-cause ng side effects. Okay, immediate side effects. So, i-infuse na lang natin. Or di kaya class, it's going to cause pain sa patient natin. So, instead class na ibibigay ko siya ng isang push, ang hapdi kasi pag pinupush ang gamot, ramdam na ramdam yan, lalo na pag antibiotics. So, that's why class, some antibiotics, instead na ibibigay siya via push, ini-infuse na lang siya. Ini-reconstitute siya sa isang bag. Okay, tapos i-infuse sa patient natin. Right? So, some drugs are given as short infusions for loading dose. Usually, either 30 minutes or 1 hour, 60 minutes. Most often than not, class, ang infusion ng loading dose natin is 1 hour. Bakit? It simplifies the formula. Okay? At saka mas madali pag 1 hour na lang yan. Okay? Kasi diba ang K sub 0 is dose over infusion time. So, at least kung 1 hour yun, whatever your K sub 0 is, yun na rin yung dose na gagamitin mo. Okay? Yung ito kasi, diba? Asan na yun? K sub 0, this is dose over T. So, kasi kung yan ay 0.5, magbabago pa tong dose mo. So, mag-i-issue, magdo-double yun. So, ang ginagawa na lang natin is, para mas simplify ang formula, pag naging 1 hour na lang kasi itong infusion time ko, if this one becomes 1 hour, then whatever dose I get, whatever K sub 0 I get pala, will be the same dose na lang. Okay? So, kung milligram per hour yun, yun na yun. Okay? Kumbaga yun na yung dose na gagamitin natin. So, are we good? And the formula for this class would be simply, same naman, pretty much. Okay? K sub 0 over clearance, rate of input over drug output, times 1 minus E negative KT. Yun nga lang, class, this time, ang T na to, alam ko na kung ano. Nilimit ko yan to either 0.5 to 1 hour. Okay, sabi natin, 30 to 60 minutes. We prefer to use hours here. Okay, we don't usually use minutes as a unit here. Pero pwede rin naman, walang problema. Okay? So, pretty much the same thing, right? Okay, ganun pa rin naman yan. So yun na nga. So K sub 0 is a dose over T. T here refers to infusion time. Okay, or infusion period. Okay, class. Now let's talk about the intermittent IV infusion. Now ano bang meron sa intermittent IV infusion? So if you can remember, class, di ba sabi natin kanina, some loading doses can be given, loading dose of drugs can be given as infusions, short infusions, usually 0.5 to 1 hour. Okay? However, class, hindi lang naman siya nalilimit sa isang loading dose. Some drugs, class, are given via IV infusion intermittently. What do I mean by this? I-infuse siya for 1 hour, okay? Pero may dosing interval yung gamot na yon. Okay? A good example of this, class, again, would be vancomycin aminoglycosides. Right? Ang nangyayari dyan, class, is something like this. If this is the plasma level, if this is the plasma level time curve, okay, ang nangyayari dyan, class, is mag-i-infuse muna ako ng gamot. Bakit ko siya i-infuse? Well, again, for so many reasons. Pwedeng number 1, masakit, okay, ang drug. Number 2, lumalabas agad ang side effects pag binigay ko siya as push. So, hindi ko siya pwede ibigay push, bibigay ko siya as infusion. So, to be on the safe side, bibigay ko siya as infusion usually for 1 hour. Alright? Now, infuse mo siya, class, for 1 hour. Ang nangyayari is, dahan-dahan umaakyat yung concentration ng gamot. Okay? Now, usually, after tumigil ang infusion na yun, okay, it's going to reach a peak. So, ito yung from 0 to T. That's my T. That's my infusion time. Okay? After I stop the infusion, dahil naubos na yan, ano mangyayari sa gamot ko? Okay, my drug class is going to eliminate following first order kinetics. Pero di ba, sabi natin, okay, if this is the MEC, ayaw natin bumaba yan below the MEC. So what do I do? So from this point now, this will now be my dosing interval. I'm going to administer another dose. So paano yun? Ano yung dose na bibigay ko? Paano ko ibibigay yung dose? So I'll give it as infusion ulit. So aangat siya pag ganito. Okay. So class, kung ano yung height nito, same lang sa height nito. Provided I'm administering the drug at the same dose or rate of infusion. Okay? So again, pag-angat na yan, that's again my infusion time. So from this, so assuming, class, this one from here to here, this is 1 hour. Alright? So therefore, from here to here, this is also equal to 1 hour. And then syempre, dahil tumigil na naman ako after 1 hour, bababa na naman siya after a certain point. Okay? And then this one again with my next dosing interval. And so on and so forth. So ang lalabas yan parang ganito. Okay? Tapos dosing interval ulit. Tapos infusion ulit. Okay? Rate of infusion. Titaw, ha? Magkakaiba yan. Okay? Until you reach steady state concentration. Right? So ang nangyari lang dito, class, parang binibigay ko siya as isa na bigay ko siya as IV push. Yung kanyang example natin, pinakaunang ginawa ng example, okay, I'm giving the drug as infusions, intermittent infusions. Short infusions, pero intermittently, may dosing interval siya. Okay, so yan yung pag-uusapan natin ngayon dito. Alright? Now, intermittent IV infusions, class, is a method of successive short IV drug infusions in which the drug is given by IV infusion for a short period, and this short period is usually between 0.5 to 1 hour. Okay? Again, for simplicity's sake, class, naawa kayo sa sarili niyo. Hanggat maaari, sabihin mo kay Doc, Doc, 1 hour na lang, Doc. Okay, kung 0.5 pagpilitan ni Doc na 0.5, sabihin mo, Doc, ikaw mag-compute. Hindi, biro lang. Madali naman mag-adjust ko sakali. Pero mas madali kasi talaga pag 1 hour lang. At saka ito naman yung usual na ginagamit. But if the doctor wants it 0.5, no problem. Okay, kaya mo naman compute yung class. Right? So, yun, short period of time followed by a drug elimination period. Then, followed by another short IV infusion. So, di ba yun na ngayon? Nagbigay ka, pinahiya mo mag-eliminate ng drug, tapos magbigay ko ulit ng infusion, hiya mo ulit mag-eliminate, infuse, eliminate, infuse, eliminate. So, in drug regimens involving short IV infusions, the drug may not reach steady state. So, the rationale for intermittent IV infusion is to prevent transient high drug concentrations. Okay? Kasi ayaw nating biglaang magkaroon ng side effects ang gamot. Kung vancomycin yun, pag pinush ko yan, magkakaroon ng extravasation ng patient ko. Pag nasyado ko naman mabilis, in-infuse ang ang drug, pwede naman mag-Regimen syndrome yung patient ko. Magkaroon siya ng allergic reaction towards it. Alright? So, ayun, transient high drug concentrations and accompanying side effects. So, many drugs are better tolerated when infused slowly over time compared to IV bolus dosing. That's why between the two class, intermittent IV infusion versus IV bolus dosing, mas practical gamitin ng intermittent IV infusion. Mas mahirap mag-compute sa ating mga pharmacies, pero mas practical siyang gamitin clinically. Okay? Okay. Now, let's go to the meat of our topic for the day, for this one. Okay? For drugs that require longer infusion time, so we use intervals called intermittent IV infusions. So, the formula for Cmax1 and Cmin1, lalabas ulit yan kasi you'll be giving the drug multiple times. Lalabas ulit ang terms na Cmax1, Cmax2, Cmax3, and their corresponding Cmins. Okay. So, class for Cmax1, ang formula lang naman dyan is, well, obviously, kung kailan ka nag-infuse. So, ang mangyayari dyan, class, if this is it, okay, nag-infuse ako hanggang dito. This is now my Cmax1. Tama? Asayaan ko siya mag-eliminate following first order kinetics. Siyempre, hindi ko naman hayaan mag-fully eliminate yan. So, bigay ulit ako ng bagong infusion. Okay, hanggang dito. This is tau. This is t. This is 0. Yeah, t. Okay? And then, allow ko ulit mag-eliminate. So, this will be now my Cmax2. This one is my Cmin1. And this is my Cmin2. So, the formula class for Cmax1 is pretty much similar to the formula na ginagamit natin sa continuous IV infusion. Yun nga lang, determined ko na yung T na to. Itong infusion time na to. Alam ko na yan. And that is usually 1 hour. 0.5, sorry. 0.5 to 1 hour. Again, depende yan ha. Pwede rin naman 2 hours to. Okay? So, that will be the equation for Cmax1. And for Cmin1, is as simple as yung equation kayo na sa IV push. Cmax1, E negative K, tau. Okay, I think that makes sense naman na, right? Kasi ang Cmin1, ito yung kanyang time na yon. Kung anong time na yan. Alright? So, that's the formula for Cmin1. Okay. Now, what about the formula for Cmax at any given number of infusions? Or Cmax-N. Okay, kaya na may Cmax-N din tayo sa IV push. Pero ang difference lang, class, sa push kanina, itong side na to, oops. Okay, itong K sub 0 over CLT is dose over VD. Yun lang. Kasi this time, kasi it's an infusion, so, ang nangyari, class, is, ganito na itsura niya. K sub 0, allow me to rewrite this na lang. Para mas clear siya. Baka may kasi kung linear na ganyan, hindi natin mag-gets. So, K sub 0 over clearance times, mahaba-haba to, 1 minus E negative KT. This is the accumulation factor for infusion. Right? Yung term na ginamit natin. Pero again, hindi naman talaga yun. Then we have 1 minus E negative NK tau. Uy, lumabas ulit siya. Over 1 minus E negative K tau. Now again, ano ito? This is the accumulation factor if you're giving the drug multiple times. Okay? Intermittently. Itong AF natin na ito, para lang to sa continuous infusion. Alright? Pero this one, the 1 minus E negative NK tau over 1 minus E negative K tau is the accumulation factor if the drug is being given multiple times. Alright? So, babalik talaga yan. Okay? Now, of course, the formula for Cmax, when N becomes very large, is 1 minus E negative NK tau approaches 1. So, therefore, class, ang magiging formula natin is, ganito na lang. 1 minus E negative KT over 1 minus E negative K tau. Nawala si 1 minus E negative NK tau kasi magiging 1 na yung value nun. Alright, so I don't think I have to rewrite that pa, no? So, it's just as simple as that. Okay? Now, formula for concentration at any given time after CSS has been reached. Ito yan. Ang nangyari dito, class, is mag-drawing na lang tayo para mas ano. Assuming, class, that the drug is already at CSS. So, obviously, ito itsura niyan. Okay? Ito yung infusion. This is tau. Tau. This is T, infusion rate. So, infuse ulit ako. Tapos, ito. Okay. Tau. Okay? So, class, after CSS has been reached, so, ang formula dyan, class, would be, ang dinagdag ko lang dito is E minus KT prime. Ano yun? T prime here, class, the total hours drug was allowed to be eliminated before reaching the next dosing interval. So, therefore, class, ang titingnan ko lang lagi dito is, asan yung peak? Kaya nga, ito, andito yung formula na to. Okay, this is the formula for C peak SS. Alright. So, ito yon. C peak SS. This is CP SS. Tapos, gano ang T prime na yan is, gano katagal ko siya hinayaang na-eliminate before reaching the next dose. So, before here, before reaching this point here, usually andito lang yan, yung T prime na yan. So, bahala ka na. Gano katagal mo hinayaang mag-eliminate after reaching the peak concentrations. Okay, so say for example, after reaching the peak concentration, drug was allowed to eliminate for 4 hours. Tapos ang dosing interval ko is every 8 hours. So, tatanungin ka, what's the resulting plasma concentration 4 hours after reaching the peak concentration? Okay, so ganun yun. Alright, so I hope you get that. Anyway, so class E negative K T prime. Kaya ako lang nilagyan ng T prime para hindi tayo malito sa T lang, which is the infusion, and then the tau, which is the dosing interval. So T prime na yan is the total amount of time I allowed the drug to eliminate after reaching the peak. Okay, and then this T prime is usually before the next dosing interval. Alright? What about the formula for C mean at steady state? Okay, madali lang din naman yan. Pero tingnan nyo, bongga. Para katulad nung kanina, pero this time, instead of T prime, T double prime. Quote yan. Alright? So, ano yung T double prime na yan? Okay, this is tau minus T. Okay? Where T prime is equal to the interval minus the duration of infusion. Now, why do I subtract the infusion time to my tau? Kasi remember, class, the only time that I allow my drug to eliminate is after reaching this point here. Okay? The infusion time. Diba? That's 0 to T. Tapos, hayaan mag-eliminate. Okay? Then this is the tau, right? Right? Pero that's, sabi natin kasi ang tau na to is 8 hours. Okay? Kasi ito yung Cmax. CPSS na lang. Kunwari, CPSS na to, ha? So, this will be my C min SS. Ito. Yan. Okay? Now, class, bakit kailangan kong isubtract si tau kay T? Kasi tingnan nyo, class, oh. Hinayaan ko ba ma-eliminate yung drug for 8 hours? No. Kasi during the first hour, kung 1 hour ito, kunwari, 1 hour. 1 hour yung infusion time ko. For the first hour, I'm actually administering the drug. So, therefore, class, kailangan ko isubtract yung 1 hour na to sa 7 hours. So, ang total duration ng class that I allowed my drug to eliminate is 7 hours. Kaya nga paulit-ulit ko sasabihin sa inyo, mas dumadali equation ang solving natin kung 1 hour lang ang infusion time. Okay, pero again, depende sa requirements ng doktor. Huwag tayo makipag-away sa gano'n. Minsan gusto talaga nila mabilisan. Basta check nyo lang kung pwede ba ang drug imabilisan. Vancomycin, minimum niya is 1 hour talaga. Okay, the usual is 2 hours infusion. Okay, pwede 1 hour pero advisable lang 2 hours. Okay? So, kaya siya ganon. Kaya ganon yung formula here. Alright? When computing for C mean SS. Tapos ito, this is C peak SS. Alright? Okay. Alright, class. So, now let's proceed to a sample problem here. So, given na rin naman ang mga kailangan ko dito. Now, one thing lang nga pala, this should not be 6. This should be 10. Okay? This is 10 milligrams per liter. Alright? Ay, palitan ko pala ng color. Why am I using that one? This should be 10 milligrams per liter. Okay? Namali pa ako ng kopya ng desired CPSS. Anyway, so that should be 10 milligrams per liter. Alright? So the problem is patient XY is a 35-year-old male with an unknown infection and weighs 70 kg with a normal renal function. So the patient will be given gentamicin. Okay, so the questions would be what should be the dose of the patient and determine the C min SS. So with this in mind, class, it's important that we use we understand the problem here. So we are looking for the dose. So obviously, class, we're going to look for XO. Okay, pero to get XO, I need my K sub 0. Okay, so to get that, usually ang formula na ginagamit natin would be CPSS equals K sub 0 over clearance times, hiwalay na natin para kita siya, 1 minus E negative KT over 1 minus E negative K tau. So I need here my K sub 0. So what do? I need to transpose the formula. Okay, so cross multiply K sub 0 times 1 minus E negative KT, bit niya yan, kasi part siya ng numerator, equals CPSS, desired CPSS, times clearance, times 1 minus E negative K tau. So, kailangan ko lang ang K sub 0. Tanggalin natin itong 1 minus E negative KT. That's 1 minus E negative KT. So, cancel out. So, matitira na lang is K sub 0. Now, class, with that, compute na tayo. So, do I have CPSS? Yes. The desired is 10 milligrams per liter times clearance, which is VDK. So, do we have VD? It's the VD 0.24 liters per kilogram times my patient is 70 kilograms. Sorry kasi hindi ako nagsusulat ng given. So, I think naiintindihan nyo naman na. Okay, kung paano natin sinosolve to. This would give us 16.8 liters. Right, so that's my VD. Sabay ko na rin K. Kailangan ko rin ng K eh. 0.693 divided by the half-life. Divided by 2 hours. 693 divided by 2. So it's 0.3465 per hour. Okay, 0.3465. Okay, good. Okay, so my VD would be 16.8 liters times 0.3465 per hour. That's for my clearance times 1 minus E negative 0.3465 times 1 hour. Okay, because its infusion time is 60 minutes. That's equivalent to 1 hour. Oh, sorry, it's tau. Ano ba yan? It should be 8. 8 hours. Okay, over 1 minus E negative 0.3465. Yun, times 1 dito sa ilalim. Okay, unti-untiin lang natin siya para makita nyo ang ang mga resulting computations. So 16.8 times 0.3465. 5.8212 liters per hour times 1 minus E negative 0.3465 times 8. 0.9375 over 1 minus E 3465. $0.2928. Okay, so 10 times 5.8212 times 0.9375, you get 54.9 5738 divided by 0.2928. 0.2928. At ang lalabas ay 186.39 35, whatever, milligrams. Okay? Or pwede mo rin i-round off to. Okay, again, depende sa'yo. Okay, so kaya nilagay ko dyan, or 190 milligrams. So this is the dose that I'll be using. Okay, folks. Okay. Now, next question is how determine C mean SS. Okay, so to determine C mean SS class, excuse me, depende to sa kung anong, excuse me. Okay. So what I would usually do here, class, is, alam ko naman ang desired CPSS ko, which is 10. So I already have my CPSS. So times E negative KT double prime na lang yan. Okay? So for my C min SS, sabi natin CPSS times E negative KT double prime. So CPSS ko, if I'm using 186.39, well, obviously ang CPSS ko dyan will be 10. So times E negative 0.3465 times 7 hours. I think alam niyo na paano ko nakuha 7 hours, right? T double prime is simply tau minus T. And that's 8 minus 1, 7 hours. Okay? So equals negative 0.3465 times 7. 10 times x na lang. 0.0884. 10. Obviously, it's going to give you 0.8843 milligrams per liter. Okay? So, yun siya. Now, class, if you want to get 4.9, determine nyo ang Cmax, ang resulting peak concentration if you use 190 milligrams. Now, class, before I forget nga pala, K sub 0 to, so this should be milligrams per hour. Now, diniretso ko na lang na milligrams na lang because ang infusion time naman natin is 1 hour. Okay, since our infusion time is 1 hour, okay, so ang K sub 0 kasi is, sabi natin, K sub 0 is dose over T. So, dahil alam kong 1 hour na yan, so automatic, whatever I get from my K sub 0, yun na rin yung dose na gagamitin ko. Okay? Kaya hindi ko na nilagay, kaya niretso ko na agad na, XO. Okay? Kasi na-assume ko na agad na, since 1 hour naman ang infusion time ko, so, it makes life simpler. Okay? Now, class, if you want to derive the, how did I get 0.902, you can do this on your own na. Okay? Basta ang ginamit yung dose is 190. Determine na lang its peak concentration. Pag gumamit ako ng 190, tapos from that peak concentration, determine mo yung Cmin. Alright? Okay, so I know that was a lot to take in. More than 2 hours na lecture to. Yeah, almost 3 hours na pala. Okay, so I hope you learned something new, class, and you can apply this okay, when you start practicing na. Okay, a lot of my students, especially in clinical pharmacy, okay, mga PharmD students ko before, okay, they really appreciate this part of the lecture. So I hope you can appreciate it too. Okay, so I'll be giving you guys seat works regarding this so that you can practice. Okay, so with that, thank you very much for listening. Hope you learned something new today.